Right. So all of you confirm me. Can you hear me, all of you? Right. Very good evening to all. So we'll start our class. Fine. So I think in my last class, I was discussing about the necessity of a starter, why we need a starter, right? So if you just look into the necessity, as the name suggests, the purpose of starter is not for starting a three-phase induction motor, but it is to limit the high starting currents, right? We have seen all the story, right? Finally, we are able to classify the types of starters, right? See, types of starters. So today is day 13, if I'm correct. Day 13. Right. Fine. So types of starters. So listen, whatever the starters we are trying to discuss now, so these starters are applicable only for cage rotor. Why? Because already I told you that whatever the resistance that is there in the rotor circuit of a slip ring, that additional resistance can be used as a starter. So these starters generally we don't use for slip ring. So whatever the starters I'm trying to talk now, they are applicable only for cage rotor, right? Done. So before I proceed, what are the equations we have discussed yesterday? One is the ratio of starting torque to full load torque is equal to IST by IFL whole square into SF. This is one equation that is needed in all the starting methods. The other one is ISC. ISC is nothing but the applied voltage per phase by the motor impedance Z01. So already I told you this is the current that would flow in the motor winding with rated voltage and rated frequency. So it is how much? 5 to 8 times the full load current. And if such high current flows, then obviously the windings will get damaged. So in order to limit motor winding against to such high currents, we need a starters, right? Now let us go for the types of starters. Types of starters. Types of starters. See, these starters are divided into two categories. One is the full voltage starter. The other one is the reduced voltage starter. So you may not be knowing the classification, what are called as full voltage and reduced voltage. First, what I'll try to do means I'll try to classify the starters the way you know. After that, we'll see which comes under full voltage starter and which comes under reduced voltage starting. Right? The first starter is the direct online starting. Direct online starters. Direct starters. And these are very much familiar with the name dual starters, dual starters. The second one is variable reactors. Variable reactors are resistor starters. Next one is, yesterday one of the student was asking auto transformer starting. The next one is star delta starters. Star delta starters. These are the classification of starters. In this, which comes under full voltage starting means, so this comes under full voltage starting. The first one comes under full voltage starting. The remaining 2, 3, 4 comes under reduced voltage starting. What is the meaning of that? We'll explain. Reduced voltage starting. Right? Now let us go one by one. Now here, before I start with, I'll take one example. With respect to that, I'll explain all the starting methods. See, I'm considering one induction motor. This is the induction motor. A 5 HP induction motor. So here the ratings are something like 400 volts, 50 hertz, say 4 pole, 20 amperes star connected winding. So this is the motor which we have designed. So let me explain the importance of each value. So 400 volts means the safest voltage what we can apply between the lines is 400 volts. Why? Because whatever that insulation that is coated around the conductor or conductor and conductor has the capacity to withstand safely the voltage is up to 400 volts. So that is the indirect communication by the manufacturer to the customer that we are supposed to apply the rated voltage up to 400 but not beyond 400. So it is a 4 pole machine. The frequency of that AC current should be 50 hertz and 20 amperes. What is the meaning of 20 amperes means? You are not supposed to load the motor. The windings are not supposed to carry the current more than 20 amperes. The safest current the windings can carry is up to 20 amperes. Why? Because whatever the insulation we are using has a capacity to bear the temperatures up to 20 amperes of current. If the currents are more than 20 amperes, then the ohmic losses will be more, the temperature will be more, and that insulation will melt and windings will get damaged. So you are not supposed to load the motor with the currents more than 20 amperes. So this is a strict rule that has to be followed, that we should not load the motor with the currents more than 20 amperes. That means at any condition, starting, running, sleeping, dancing, whatever it may be, the windings are not supposed to carry the currents more than 20 amperes. So this is the significance of that nameplate details. Is it clear? Confirm me. Is it clear? Confirm me. But fortunately or unfortunately, knowingly or unknowingly, if I take this motor and if I start this motor, start this motor, then the starting current will be 5 to 8 times of full load current. If you are going to start the motor directly with which voltage? 400 volts, it will draw 5 to 8 times. So in this case, 100 amperes to 160 amperes of current, the windings will carry during starting. But the windings are designed to carry the safest current of 20 amperes. But very unfortunately, at rated voltage at starting, the windings are carrying 100 to 160. In this case, 100 to 160. But those windings are designed only to carry the safest current of 100 amperes at any conditions, maybe starting, running, dancing, sleeping, whatever it may be. So they are supposed to carry up to only 20 amperes. But very unfortunately, if I'm going to start the motor with rated voltage, then what will be the current? It is 5 to 8 times of full load current. What is the full load current of this motor? 20 amperes. Then it will carry the current 5 to 8 times of full load current. The motor windings will carry 100 to 160 amperes in between. And if such high current flows, what happened to that ohmic losses in the windings will be more. The temperatures will be very high, that insulation will melt and windings will get damaged. So in order to protect the motor winding against to such high currents, we need a starter. We need a starter. Is this point clear? Confirm me. Confirm me. Right. Done. Thank you. Right. Done. Fine. Now what I need to do means I need to control such high currents which are flowing in the windings during starting. So I need to have a starter. I hope you understood the significance of starter. Is it clear? Confirm me. Confirm me. All of you raise the hands. Right. Right. So all windings means all windings will get damaged. Right. Done. Now let me proceed. So now I'm talking about DOL starting, direct online starting, direct online starting. So what is this direct online starting means? So this comes under which type of starter? Full voltage starting, full voltage starting, full voltage starting. So what is the meaning of this full voltage starting means? So using this DOL starters, we are going to start the motor directly with rated voltage. What is the meaning of rated voltage? We are going to start the motor directly with 400 volts. Sir, just now you told that if the motor is started directly with rated voltage, as there is no load impedance, as the relative speed between feed and the rotor conductors is maximum, the flux cuttings will be maximum, the rotor currents will be maximum, and in this case it is 100 to 160 amperes. And if such high currents are flowing in the motor windings, definitely the ohmic losses will be high, the temperatures will be high, that insulation will melt, and windings will get damaged for sure. You know that this is going to happen when you are going to start the motor with a directly rated voltage, right? But even after knowing that how much dare you should have that you are going to start the motor directly with rated voltage. Sir, is this statement clear that in case of DOL, we are going to start the motor directly with rated voltage? Yes, I'm very much clear and I'm very much conscious that whenever I'm using the terminology full voltage starting means this motor is started directly with rated voltage for sure. So in case of DOL starter, the motor is started directly with rated voltage, right? Please keep this point in the mind. Sir, if that is the case, we agree that in this case, the motor is started directly with rated voltage. If so, see, someone is raising the hands. Is my audio, video and everything are clear? Is there any strucking and other things? No. No, it may be from the other side. Please check your network connection, Baba. From my side, it is clear, right? Please. So here we are going to start the motor directly with rated voltage. Listen. So in case of DOL starter, we are going to start the motor directly with rated voltage. Sir, if you are going to start the motor directly with rated voltage, definitely the windings will be damaged. No, in this case, the windings will not be damaged. Sir, if that is the case, if the windings are not damaging, then there will be some internal mechanism to control such high currents. No, there is no internal mechanism in case of DOL. The windings will carry 5 to 8 times the full load current, right? In this case. So even after carrying that windings will be safe. Sir, how come, sir? We agree that in case of DOL starting, the motor is started directly with rated voltage. We agree that. Second thing, you told that there is no mechanism to limit such high currents using the DOL. So the windings will carry 5 to 8 times the full load current. Even this also we agree. But you told that the windings will be safe even after carrying such high currents. How come it is possible, sir? After carrying a high current of 5 to 8 times the full load current, how come the windings will be safe? Can you please explain how the windings will be safe? Yes, I'll explain. Even after carrying 5 to 8 times the full load current, how come the windings will be safe, particularly in case of DOL starting? I think this point is clear, right? We'll see that why the windings will be safe after carrying a current of 5 to 8 times the full load current. So this concept I'll be explaining after some time. Why Bahubalu killed that? Why Kattappa killed the Bahubali, right? We'll see the logic behind that later. But let me explain the significance of this DOL starter first. So in case of DOL starter, we don't have any mechanism to control such high starting current. Even though we have DOL starting, there is no DOL starting, the windings will carry the same 5 to 8 times the full load current. But what is the special thing or important thing in this DOL starter means there is a protection against two things. One is overload, overload. The other one is low voltage protection. Overload and low voltage protection. What do you mean by overload? See, so the induction motor is started without any load. Then slowly I'm increasing the load on the motor. When we are increasing the load on the motor, the current drawn from the supply, the current carrying by those conductors will increase. A situation will come when you are loading the motor fully, the windings will carry the rated value, say in this case 20 amperes. But without looking into that current, if you are going to load the motor beyond that full load, even beyond that full load, the motor will continue to rotate till maximum torque. But if you are going to load the motor beyond the full load value, the windings will be more than the rated value. If the windings are more than the rated value, then the temperatures will be very high and there is a possibility that the windings will get damaged. So in that case, there will be a relay which continuously monitor the currents, and if those currents are more than the rated current, then that relay will trip the motor from the source and hence the windings will be safe, right? So there is a protection against to the motor winding because of that high currents when the motor is overloaded, right? So I think what is the meaning of overloading? What is the meaning of overloading is loading the motor beyond its rated value. Then you may have a doubt, sir, if you load the motor beyond its rated value, will it supply the required load torque? Yes. Up to what value it will supply? Up to maximum torque. But what is the main problem we are having? If you are loading the motor beyond the full load torque, the windings will carry the currents more than rated. And in that case, the ohmic losses will be high, the temperatures will be high, the windings may get damaged. So there has to be continuous monitoring mechanism which monitors the current, and if those currents are more than the rated current, then it has to trip the motor from the source and hence the windings will be safe. So such monitoring mechanism, such relay concept will be there in DOL starter, which it trips the motor from the source when that motor is loaded beyond its rated value, when the motor is loaded beyond its full load capacity. Why? Because beyond its rated value, the windings will carry currents more than its rated value, safest value. In these cases, the relay will trip the motor from the source and windings will be safe. I hope this point is clear. Confirming. Confirming. Right. 1 second. Right. In the second case, low voltage. Low voltage. What is the meaning of low voltage? Say the mechanical load is constant. When the mechanical load is constant, the required power to supply that mechanical load will remain constant. So what is the equation for that? Active power drawn from the source VI cos phi. So to supply the required mechanical torque, the active power drawn is VI cos phi. Fortunately or unfortunately, say because of something, the input voltage is reduced. The input voltage is reduced, but the mechanical load is constant. This required power should remain constant. So whenever there is a reduction in voltage, obviously for the same power, the motor will draw very high currents. So when the motor is subjected to low voltage with a load on the motor, then the motor will draw very high currents. And if these high currents are dominating the rated value, or if they are crossing the rated value, then obviously the relay will trip the motor from the source and windings will be safe. So can I say like this? It may be the overload condition or it may be the low voltage conditions. In both the cases, the windings will draw currents more than their rated value. And if the windings are carrying the currents more than rated value, there has to be a tripping mechanism so that the windings will be safe. So the relay which is placed in the DOL starter will do the role of tripping the circuit, tripping the motor from the source when the windings are carrying the currents more than rated value. So like that, we have a protection over high currents due to overload and due to low voltage condition. So the motor windings should be protected when you are overloading the motor or when the motor is subjected to low voltages. In both the cases, the windings will carry the currents more than rated, and in that case, that relay will be tripping the motor from the source and windings will be safe. I hope this point is clear. Confirm me, all of you. Right, right. Only few what happens to others. Please raise the hands. Right. So as of now, if anyone says, "Array, your sir told that in case of DOL starter, we don't have any mechanism to limit the high starting current. That means the motor will draw high currents, right? In case of DOL, right? But the windings will be safe. But what is the additional benefit we are having in case of DOL starting means it is not to limit the current during starting, but to protect the motor windings during running condition. Running condition. What happened? See, I'm clear. Please text me if everything is clear. Right, right, it is clear. Right, fine. Right. This is something about your direct online. So can I say in DOL starting, in dual starter, the windings are protected. Windings are protected from high currents due to overload low voltage conditions. Low voltage conditions. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. Raise your hands. Right. Fine. Sir, we agree that there is protection for the windings during running. Okay, sir. First, you tell during starting. When the one not safe during starting, why you are talking about running conditions? Unless and until the windings are safe starting, we cannot talk about running condition. You told that if you are going to start the motor directly with the rated voltage, the windings will carry 5 to 8 times of full load current. Even after carrying such high currents, how the windings will be safe? Sir, can you please tell me? Running conditions, we understood that there will be a relay, and the role of that relay is to trip the windings when the windings are carrying the currents more than their rated value, right? Fine. Sir, can you say again about low voltage? See, voice is breaking. Vishnu, Ajit, from my side, I am clear. Vishnu, you check. See, low voltage means the load on the motor is constant. When the load on the motor is constant, the active power drawn from the source should remain constant. When the active power should remain constant, whenever the motor is subjected to low voltages, whenever the motor is subjected to low voltages for the same active power, the current drawn will be increased. And if these currents are right, 1 second, I'll disconnect and I'll connect. Wait. Now I think it is clear. Confirm me. It is clear. Confirm me. Raise the hands. Right. So whenever I'm using this video, so because of that video, it is taking more net. Right. Anyhow, fine. I'll come back. Right. So we agree during running condition, there is a relay. The relay will monitor the winding current. If those currents are finding more than the rated current, then it will be tripped. Then now can you please explain during starting why even after carrying such high currents, the windings will be safe? Windings will be safe, right? So the first point to be noted here is, so these device starters are used for low HP motors, generally less than 5 HP, low HP motors, small size motors. And you know that in case of low HP motors, still the problem is not clear. See, some people are raising the hands. It is clear. Just confirm me. Yes. Right. Done. So it is clear. Right. Pawan, it is from your side, Pawan. Right. See, other people are saying clear. So it is your side, Pawan. Try to rectify, Pawan. Right. Fine. Now it is used for low HP motors, generally less than 5 HP motors. If you recall the types of slots, I told you that for low HP motors, we used closed slots. For low HP motors, we use closed slots. This was already explained to you. And in closed slots compared to other slots, the leakage reactance will be very high. Don't ask now. Why? Because that was already explained. When the leakage reactance is very high, the starting current, which is directly proportional to V by R plus the leakages, because of this high leakage reactance, the starting current will be less. Partially, we are able to control the starting currents. What do you mean by that? See, in this case, I told you that the starting current will be ranging from 5 to 8 times of full load current. Now let us consider in our example, these windings are carrying a starting current of 100 amperes. 100 amperes. Let us take 100 amperes when we are starting the motor with 400 volts. Let me take. So what is the starting current drawn will be 100 amperes. Let us consider. So here, if you are using closed slots, then the starting current will be less. What do you mean by less? Less. See, if this is a current drawn by the motor with open slots, what is the current that is drawn by the motor with open slots? Let it be 100 amperes. Then if the motor is using closed slots, the current will be something like 90 amperes. Let it be 90 amperes. Let it be 90 amperes. So if anyone questions you which slot motor will draw comparatively less starting current, means closed slots. Why? Because the leakage reactance offered by that at starting will be very high and hence the starting current drawn will be less. So here, as we are using closed slots compared to other slots, the starting currents will be less, right? As the starting currents are less, how much less? Instead of drawing 100 amperes, say it is drawing 90 amperes. That means when compared to 100 amperes, we are able to reduce that current partially to 90, but that 90 is still higher. What is the safest current the windings has to carry means it is only up to 20 amperes. But 90 amperes is still more than 20 amperes. But when compared to that 100 amperes, we are successful in limiting the current partially. From 100, we are making the current to flow only 90. We are able to limit the current partially. Why? Because what is the slots we are using in low HP motors means closed slots. I hope it is clear. So if anyone questions you, alright, it is true that the windings will carry the currents 5 to 8 times the full load current, right? When you are going to start the motor directly with rated voltage, yes. Then how can you say the windings will be safe even after carrying such high currents? Means the first point to be noted here is these DOL starters are used only for low HP motors. In low HP motors, as we are using closed slots, the leakage reactance of the closed slots compared to other slots will be more, and hence the starting current will be comparatively less, but not to the extent of less than 20 amperes. So it is less compared to that 100 amperes, it is less. So we are able to limit such high currents partially, not to the extent of less than full load current. We are able to limit such high currents partially. Why? Because what are the slots we are using means closed slots. Is this point clear? Confirm me, love. Is this point clear? Confirm. Right. Right. But still that 90 amperes of current is high. Still that 90 amperes of current is high. Then how the windings will be safe after carrying such high current means I'll answer to this question. Please see. I told you that these are used for low HP motors. Low HP motors. For low HP motors, the size of the machine will be less. The rotor diameter will be less compared to a high HP motor. So this is a high HP motor. In case of high HP motor, the diameter will be more. So this is a low HP motor and this is a high HP motor. High HP motor. So in which case the size will be more, means in high HP motor the size will be more, right? So here the inertia will be less. Inertia is less. And here the inertia will be high or inertia will be more. I hope this point is clear. So which motor will be having more inertia means high HP motor. Why? Because the rotor size will be more, rotor weight will be more, the inertia will be more in case of high HP motor. Is this point clear? Confirm me. Confirm me. Raise the hands. Right. Good. Then who is the main culprit for such high starting currents? Who is the main culprit? This stupid fellow R2 into 1 by S minus 1. This fellow is 0 in the rotor circuit. As this fellow is 0 in the rotor circuit, the rotor impedance is very less, the rotor currents are very high, the stator currents are very high. Why this fellow is 0 at starting means the rotor speed is 0, the slip is 1. That is the reason this fellow load impedance is 0, the motor impedance will be less, and hence the starting current drawn from the supply will be very, very high. The starting currents will be very high, right? So who is the main culprit for such high starting current means the load impedance. See, Baba, I'm clear with my network. So many people are just 5, 6 people are raising. So please try to rectify your network. See, I told you that if all are raising, then it is the issue from my side. But few are just raising. Please remember that. Right, done. So who is the main culprit for such high starting current means the load impedance. That fellow is not there in the rotor circuit during starting. Because of that, the motor windings are carrying very high currents, right? Is this point clear? Confirm me, all of you. Raise the hands. Right, right, done. Now let me see. I'll give a three-phase supply to this motor, and I'll give a three-phase supply to this motor. Let me consider. So which motor speed will increase like a impulse, which speed will shoot up like a impulse means the one with low inertia. So the low HP motor will be having lesser inertia. Then whenever you give a three-phase supply, immediately the speed will increase like a impulse. When the speed is increasing like a impulse, this slip will fall like a impulse. Then this load impedance will build up like a impulse. The motor impedance will build up like a impulse. Then such high currents will fall like a impulse. That means in case of DOL starting, as we are using this for low HP motor, as the rotor inertia is very less, as soon as you are giving a three-phase supply, the speed of the motor increase like a impulse. It will shoot up like a impulse. When it is shooting up like a impulse, such high currents will fall like a impulse. I mean to say that it is true that with this DOL starting, the windings will carry currents up to 5 to 8 times the full load current. But the fact is, such high currents are not flowing for long time. Such high currents are flowing only for very short time. As they are flowing only very for short time, then obviously the windings will be safe. When that windings will get damaged means such high currents has to flow for some time, and during that time that ohmic losses should be more, and because of that ohmic losses the temperature has to rise. But here the temperature is a lazy fellow, that fellow cannot immediately shoot up. The increase in temperature has to start melting that winding, that insulation, and windings has to be damaged. But this will take some time. Before this cycle completes, such high currents will come to normal values, and hence the windings will be safe. So that is the reason the windings will be safe. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right. I'll repeat once again. In case of DOL starting, we are going to start the motor directly with rated voltage. So when we are starting the motor directly with rated voltage, it is true that the windings will draw a currents of 5 to 8 times the full load currents during starting. So here, very definitely the windings will draw the currents 5 to 8 times the full load current during starting, but still the windings will be safe. Why even after carrying such high currents, the windings will be safe? Why the windings will be safe means, as I told you that these motors are used for low HP, and for low HP, the size will be less, right? As the size is less, the inertia will be less. So whenever you give a three-phase supply to that low HP motor, the speed will shoot up like an impulse, and such high currents will fall like an impulse. So such high currents are flowing only for very short time, and if such high currents are flowing only for short time, the windings will be safe. So that is the reason the windings will be safe in case of DOL starting. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right, done. So this is something about your DOL starting, right? But what is the main problem we are having with this DOL starting means, what is the main problem we are having with this DOL starting means, right? What is the main problem we are having with the DOL starting means, one second. Right. But what is the main problem we are having with this dual starting means? Dual starting means it is true that the windings will carry those currents only for short time. But because of these high currents which are flowing in the windings for short time, the equipments which are connected parallel to this will be having a dip in their voltages. What is the example means? See, this you might have seen sometimes. See, you want to just pump your water from your just some to the tank, then you'll be switching on the motor. As soon as you switch on the motor, you can see the dimming of the tube light. Sometimes you see the tube light will get a dim. Sometimes when you are switching on your refrigerator, the tube light will get a dim. Sometimes when you are using some another fan, another motor, you can see the tube light will get dim. That means there is a dimming of tube light when the motors are started. So here also the same thing you can see. So whenever you are going to start a three-phase induction motor directly with the rated voltage, so nothing will happen to that windings, nothing will happen to the motor, but the equipments which are connected parallel to this motor will be having a dip in the voltage during that time, and because of this dip, then those equipments may be affected. The best example is whenever you are starting a induction motor directly with online, directly with rated voltage, then you can see a dimming of tube light you might have observed. So this is the main problem. But the good thing is this dimming is only for short time, a very less time, and this less time is not going to affect the performance much. That is the reason, even if you are going to have a dimming for very short time, there is no need to worry about this starting. So the starting is permitted by the electricity people. Why? Because so it is not going to damage the own machine, and it is not going to disturb the equipments which are connected parallel to that. Now the question comes, why there will be a dimming of tube light when you are going to start the motor directly with rated voltage? I'll explain. See, you know that pole. So from that pole, we'll be getting the power supply. From the poles, we're getting the power supply. This is a service line. Let me call it as a service line. Service line. So here I'm having an induction motor connected across to this, and there is a tube light connected across to this. Right? This is a tube light. Tube light. Let me consider. So this we call it as a service line. So whenever I'm starting this motor, then the motor will draw high currents, but it is for very short time. So yes, what is the high current it will be drawing? So it is say 100 amperes. So this 100 amperes into the service line drop, service line impedance, let it be something like 0.1 ohms. Then what is the voltage that is dropped in that service line? It is something like 10 volts. The voltage that is coming to the tube light will be 220 volts. But what is the voltage that need to come to the tube light? It should be something like 230 volts. But the voltage that is coming to the tube light is 220 volts. So there is a dip in the voltage. There is a sag in the voltage. When there is a sag in the voltage, you can see the dimming of tube light. But the dimming will not be persisting for long time. It is only for short time. Why? Because these high currents will flow only for very short time. So very immediately this 100 amperes will come to 1 to 2 amperes. Then that voltage drop will drop, and that voltage will shoot up to nearly 230 volts. Again, that tube light will go bright. Right. So this is the main problem we are having if we are going to start the motor directly with dual starting. I'll repeat once again. See, please of you listen. In case of dual starting, we are not going to start the motor with reduced voltages. When we are not going to start the motor with reduced voltages, what do you mean by that? Means we are going to start the motor with rated voltage. And we know that if the motor is started directly with the rated voltage, the windings will carry the currents 5 to 8 times the full load current. And if such high currents are flowing, then obviously the windings will get damaged. But in this case, even after carrying such high currents, the windings will be safe because such high currents are flowing only for very short time, very less time. Because of that, the windings will be safe. Why that windings will get damaged after carrying high current means, so when those high currents are flowing for some time, then the ohmic losses will be more, the copper losses will be more. Due to that, the temperature will increase. When the temperature increases, that insulation will melt. When that insulation melt, then the windings will get damaged. So this will take some time. But here such high currents are not flowing for such a time. It is flowing only for very short time. That's the reason the windings will be safe even after carrying such high currents. But what is the main problem we are having with this DOL starting means, as this current has to be supplied from that common service line, so such high currents are flowing in that common service line, in that the drops will be more during that starting. As a result, the equipments which are connected parallel to this motor will see a dip in the voltages. The Because of the dip in the voltages, you can see the dimming of tube light when you start a motor direct with rated voltage during starting. So this you might have seen in many cases. I think this point is clear. Confirm me all of you. Confirm me all of you. Right. Done. So this is something about your DOL starter. Sir, why sir dim? Dim means the voltage is reduced. So for the tube light, the voltage has to be 220 as 230. If the voltage is falling less than 230, then you can see there is a dimming of tube light, right? I think this is clear. But what is a good thing we are having in case of this DOL starter means, so the windings are protected during running condition against to over voltage and against to that low voltage condition. So there is a protection against to such abnormal conditions, right? I think this point is clear. Confirm all of you. Confirm all of you. Only two. What about others? Right. Fine. Now let us go for some equations, right? So one or two again raising the hands. Let me just now finally you confirm video, audio and other things are clear. Confirm all of you. Right. So it is clear. So this is something about DOL starters. Let us go for the equations. Equation C. Equation C. This is an induction motor. What is the impedance of the motor windings during starting? Z01. Yesterday we have seen. This motor is supposed to be started directly with rated voltage, but if that is the case, the windings will carry very high currents. For that, we need a starter. So this is a DOL starter. This is a DOL starter. Starter, right? So here, let us consider we are applying V per phase. This is the per phase voltage. I told you that in case of DOL starter, there is no mechanism to drop any voltage. So what is the voltage that is applied here? V per phase only. V per phase only. So here I'm using some terminologies. ISTM. What is the ISTM means? The starting current drawn by the motor winding. And I'm using one terminology, ISTS. What that S means? The starting current drawn from the supply. So this is the common notation. So here, let me write ISTM. Starting current drawn by the motor. Starting current in motor windings. Motor windings. Similarly, ISTS, starting current drawn from the supply. Drawn from the supply. Drawn from the supply. Is this point clear? Confirm. Confirm. These are the notations. Right. See, the starting current drawn by the motor always depends upon the applied voltage and the impedance, right? So what is the starting current drawn by the motor now? The starting current drawn by the motor will always depends upon the voltage we are applying. What is the voltage you are applying? V per phase. What is the impedance? Z01. And you know that by definition, rated voltage by the impedance is nothing but ISC. That means the motor will carry a current of 5 to 8 times the full load current. 8 times the full load current. But the fact is such high current flows only for very short time, right? So here the starting current drawn by the motor winding is equal to the short circuit current of the motor. What is the short circuit current? It is the current that would flow in the motor windings with rated voltage, right? Right. So here you can see the starting current drawn by the motor and the starting current drawn from the supply both are same. There is no division, there is no like partition. So here the same current is flowing. So here the starting current drawn from the supply, the starting current drawn by the motor, both are same. So this is ISC. ISC. So here I'll be using one notation. What is that? Please see. See, the starting current drawn from the supply by a DOL starting is equal to ISC. ISC. This is one equation. Is this point clear? Confirm me. Confirm me. So what is that IST? S comma DOL means it is the starting current drawn from the supply with a DOL starting. So whenever I'm using this terminology DOL means what is the voltage you are applying? Rated voltage. Rated voltage. That means the currents will be 5 to 8 times the full load current, but those current flows only for short time. The windings will be safe. The other one is I want to find out starting torque to full load torque. Starting torque to full load torque, that is equal to IST by IFL whole square into SFL. But here you know that IST is equal to ISC. So if that is the case, the starting torque by full load torque is equal to ISC by IFL whole square into SFL. If I simplify this, I write the starting torque with the DOL starting is equal to ISC by IFL whole square into SFL into TFL. So this is one more equation. So these are the two reference equations which you are taking for all speed control techniques. Is it clear? Confirm me all of you. Is it clear? Raise the hands. Right, only few, right, all right. So this is something about your DOL starter. I'll go for some comparison table so that we can take one numerical also, right? Why? Because for every topic I'm taking one numerical. Please try to learn that, right? One numerical. What is it? Let us see. Comparison. So here the starter equations, the starting current drawn from the site in amperes, the starting torque in Newton meters. Newton meters, right? Let us see. What is the first starter here? First starter is DOL, right? So what are the equations we have this DOL starter? If you see, the starting current drawn from the supply by a DOL starter is equal to ISC. The starting torque DOL is equal to ISC by IFL whole square SFL into TFL. So these are the two equations. Is this point clear? Confirm me. Confirm me. Confirm me. All of you raise the hands. Raise the hands. Is it clear? Right. Just 1 second. Wait. I'll switch on and switch off that Wi-Fi once. Right. So now you please confirm if everything is clear. Right. See why? Because at least 1, 2 are raising the hands, which is something like creating disturbance for me. So that is the reason once on and off. So from my side, there is no issue. See, now I'll take one. What is that example means? See, this is the motor which we have designed. This is the motor which we have designed, right? This is the motor which we have designed. Let me consider that this motor is initially started with direct online. The motor which we have seen on board. So this motor is initially started with direct online. If this motor is started direct online, let us consider the starting current is 100 amperes, 100 amperes, and the torque is 100 Newton meters. These are the values, and for that motor, these are the highest values. These are the highest values for that motor, right? So these are some numericals, right? So we have done one induction motor, and that induction motor is started directly with dual start. So what are the current from the source and what are the starting torque? Means it is 100 amperes and 100 Newton meters. We'll take this one as a reference now, right? Is this point clear? Confirm? Raise the hands, all of you. Done. Next starter is the next starter is. So we'll see. The next starter is variable reactor. Variable reactor. Variable reactor or resistor starters. Resistor start, variable reactor or resistor starters. So what is the meaning of variable reactors or resistor start means? See, I'll take this induction motor, right? And this induction motor is not started directly with rated voltage, but what I'm trying to do means I'm trying to connect reactors in series with each line. Reactors in the series with each line. I'm connecting reactors. And from there, I'll be taking the supply to that motor. Like this, like this. So these we call it as series reactors. Series reactors. Series reactors. Reactors, right? Done. The significance of this series means, let me tell by taking some numericals. What is that? See, I'm applying a voltage of 100 volts per phase. Voltage I'm applying 100 volts per phase. Out of this 100 volts per phase, let me consider 10 volts is dropped here. So how much voltage is dropped? 10 volts is dropped there. Then what is the voltage that is applied here? Means it is 90 volts. So what is the logic in case of series reactors means out of a voltage V, a part of the voltage is dropped in the series reactors. When a part of the voltage is dropped, then the voltage what we are applying to the stator windings is reduced. So like this, we are going to reduce the voltage what we are applying to the winding. A part of the voltage is dropped in the reactors and the remaining voltage is applied to the stator windings. Is this point clear? Confirm me, hands. Very good. Very good. So instead of like 110, I'll tell like this. What is that? We are applying a voltage of V per here. We are applying a V per phase here. And here I'm applying a voltage of XV here. So here X is less than 1. Less than 1. So what is the meaning of less than 1? For example, say X is equal to say 0.9. When X is equal to 0.9, That means how much voltage you are applying? You are applying 90% of voltage to that stator winding. Then the 10% voltage is dropped in the series reactors, right? See, I don't know whether the problem is from my side or problem is your side. I'll come back. Wait, just I'll switch on and stuff. Right. Please confirm me now. Is it clear? All of you. Right. See, from my side, I don't think we have any issue. Again, I have just on and off, and to that Wi-Fi, no other mobiles, no other laptops have been connected. Only this is connected. Please understand. Now I'm talking about variable reactors or resistor starter. What is the logic in this means? Out of this voltage V, a part of the voltage is dropped in the reactors and the remaining voltage is applied across the stator windings, right? C. For example, say that X is equal to 0.9. So what is the meaning of that 0.9 means? You're applying 90% voltage to the stator winding and 10% is dropped in the series reactors. For example, say if X is equal to 0.5, then what is the meaning of that? You are applying 50%, then 50% is dropped in the series reactors. I hope you understood the logic behind this series reactors. A part of the voltage is dropped in the series reactors. I hope this is clear. Confirm me, all of you. Raise the hands. Right. Now let us calculate the starting current drawn by the motor winding and the starting current drawn from the supply. The starting current drawn by the motor, and this is the starting current drawn from the supply. So please, the starting current drawn from the supply motor always depends upon the applied voltage and the impedance. The starting current drawn by the motor is the voltage what we are applying by the impedance. So it is X into V by Z01. And you know V by Z01 is nothing but which current? It is ISC. It is ISC. So it is the starting current drawn by the motor. You can see it is X times that ISC. And here also the starting current drawn by the motor and the starting current drawn from the supply both are same. So here starting current drawn from the supply and the starting current drawn by the motor both are same. Both are same. So this is equal to how much? It is X into ISC. So I can write the starting current drawn from the supply by variable reactor starter is equal to X times of ISC. And what is that ISC? You know that ISC is nothing but the starting current drawn with DOL starting, right? So ISC is nothing but the starting current drawn with DOL starter. So when compared to DOL starting, you can see the current is X times, right? So if anyone questions you, when compared to DOL starting, what will be the current drawn by that variable reactor starter? It is X times, right? I'll fill that column here, right? So the second starter is variable reactor starter. VR means variable reactor starter. So the starting current drawn from the supply by variable reactor starter will be X times the starting current drawn from the supply by a DOL starting. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. Then what about the torque? What about the torque? So starting torque to full load torque is equal to IST by IFL whole square into SFL. So here IST is nothing but X times of ISC. X times of ISC. If I substitute the same thing, it is X times of ISC by IFL whole square into SFL. Then you can see I can take out this X square outside. So it is ISC by IFL whole square into SFL. Starting torque to full load torque. Then I'll rearrange this. So it is the starting torque with variable reactor starter is equal to X square into ISC by IFL whole square into SFL into TFL. But you know ISC by IFL whole square SFL into TFL is the torque with which starters? You can see DOL starters. So here the starting torque with variable reactor starter will be X square times the starting torque with DOL starter. These are only that equation gaming. That's all. Nothing more here. Only that equation plays a vital role in this case. So I'll fix here. I'll write that here. What is the starting torque with this variable reactor starter? It is X square times the starting torque with DOL starter. DOL starter. Right? I hope the equations are clear. Please confirm me. Confirm me. So if anyone questions or when compared to DOL starting, what will be the current drawn from the supply means it will be X times, or what will be the torque means it is X squared times, right? We have seen the derivative part here or derivation part here. Now the question is, it is like this. Whatever the motor we have designed, this motor is initially started with DOL starting. So with the DOL starting, what are the currents drawn? 100 amperes, and the starting torque is 100 Newton meter. Let me consider if the same motor, if it is started with a variable reactor starter with X is equal to 0.9, then what will be the starting current drawn and what will be the starting torque developed? The questions will be like this. The question will be like this. See, a three-phase induction motor is initially started with rated voltage and rated current, rated frequency and hence the currents are 100 amperes and the torques are 100 Newton meters. If that motor is started with a variable reactor starter with X is equal to 0.9, what will be the currents and what will be the torque? So that means when compared to DOL starting, what will be the currents and what will be the torques we need to find out. So I'll fill that column. See what is that? This time the same motor is started with a variable reactor starter with X is equal to 0.9. Then what will be the current? So current will be X times the DOL current. What is the DOL current? 100, X is 0.9. So it will be 90 amperes and torque will be X squared the DOL. So it is 0.9 square, it is 81 Newton meter. So if the question is like this, if the same motor is started with a variable reactor starter with X is equal to 0.9, then what will be the current drawn? What will be the torque developed means 90 amperes of current it will draw and it will develop a torque of 81 Newton meters. I hope this is clear. Confirm me all of you. Confirm me all of you. Right. See what are the drawbacks we are having this with a variable reactor starter is drawbacks is you can see the reduction in the starting torque is more compared to the reduction in starting current. Torque is reduced by X squared times, but whereas the current is reduced by only X times. So which reduction is more means torque reduction is more. So can I write reduction in torque is more. Reduction in starting torque is more compared to reduction in starting current. Torque reduces by X squared times whereas current reduces by X times. I hope this point is clear. All of you confirm me. Right. Done. The second point is see, I'm calling myself as a source and I myself has the capacity to supply active power as well as reactive power. If I'm supplying more active power compared to the reactive power, my factor will be more, it will be closer to unity. And if I'm supplying more reactive power, then my power factor will be less. It will be away from 1. I hope this point is clear. Confirm me all of you. Right. Now you take an induction motor. This induction motor is a single excited machine. As it is a single excited machine, this induction machine is connected to only a single source. And this induction motor need active power for turning the rotor and it needs the reactive power to produce a rotating magnetic field. So whatever the reactive power that is required for a rotating magnetic field, whatever the active power that is required for rotating a rotor, it will draw from the same source. So as I'm calling myself as a source, I'm supplying the active power and also the reactive power to that machine. As I'm supplying the reactive power to that machine, my power factor will be always less than 1. So the factor of mine will be less than 1. That is the reason the induction motor will always operates with lagging power factor. Why? Because it is drawing the reactive power from the same source from which it is drawing that active power. So that is the reason it is always operate with a lagging power factor. But whereas if I take a synchronous motor, the synchronous motor has the capacity to draw the reactive power from two ways. It can draw the reactive power from the source or even it can draw the reactive power from the rotor side. If it is producing if the rotor is producing the required reactive power to produce the field, it will not draw any active power, reactive power from the source. The power factor will be unity. Like that, the power factor of that synchronous motor can be either lagging, leading, or it can be unity. But whereas the power factor of an induction motor is always lagging. Why? Because it is drawing the reactive power from only one source from which it is drawing the active power. Is this point clear? Confirm me. Is this point clear? Confirming? Right. But in addition to that, we are connecting a series reactors. So these series reactors also need magnetic field, reactive power to produce the magnetic field. So from where they are drawing the reactive power means from the same source from which that induction motor is also drawing the reactive power. Then what will be the total reactive power supplied by this source now? Increase. Why? Because it has to supply the reactive power to produce the magnetic field by that reactors and also the magnetic field by that induction motor. The total reactive power of this machine, this source will be increased. As a result, what happened to the power factor of the source now? It will be reduced. So because of the series reactors, the input power factor will be reduced. Why? Because when we are connecting a series reactor, so whatever the reactive power that is required to produce the field, it is drawing from the same source. Now this source is applying the reactive power for that reactors and also for that induction motor, and hence the reactive power supplied will be increased and the power factor will be reduced. Is this point clear? Confirm me. Confirm me. Right. So can I say due to or because of the series reactor, the power factors will be reduced. So to rule out that, so these reactors are replaced with resistors. But what is the main problem we are having with that resistors means the ohmic losses will be more during starting and hence the efficiency will be less during starting. That is the main drawback, right? So here, due to series reactors, power factor reduces. To rule out that reactors are replaced with resistors, but efficiency will be less during starting, during starting, during starting. I think this point is clear. Confirm me, all of you. Raise the hands. Raise the hands. Raise the hands. Right. I'll repeat once again. See, in case of series reactor starters, what is that we are trying to do means we are going to drop a part of the voltage in the series reactors and the remaining voltage is supplied to the stator winding. As a part of the voltage is dropped in the series reactor, the voltage that is applied to the stator windings will be reduced and hence the starting currents, the starting torque will be reduced. The good thing is we are able to reduce the starting current, but the bad thing is we are going to sacrifice more starting torque. That means when we are able to control the starting current by x times, when you are able to limit the starting current by x time, but whereas the starting torque is reduced by x square times. So which reduction is more means the starting torque reduction is more. That is the reason these starters are not used when the starting torque requirement is more. For example, if the motor is with some load, that load need high torque. So, but if I'm going to start the motor with these reactors, then this motor may not be sufficient to supply the required load torque and the motor may not start. So these starters are used when there is no load or when the load on the motor is very less, we use these starters. The second point is because of the series reactors, the input power factor will be less. So to rule out that those reactors are replaced with resistors, but due to that resistor, the ohmic losses will be more and hence the efficiency of the motor during starting will be less. So this is something about your variable reactors, variable resistors. Sometimes we call it as variable impedance starters also. I hope this is clear. Confirm me, all of you. Confirm me, all of you. Right. Next one is one of the student was asking yesterday, auto transformer starting. Auto transformer starting. What is ISC, sir? ISC is the current that will flow in the motor windings with rated voltage, right? Please. Next one is auto transformer starting. Auto transformer starting. Auto transformer starting. Auto transformer starting. Today also please try to give alarm at 6:44. Just auto transformer starting. So it is a step down auto transformer. So this is a step down auto transformer. This is an induction motor. What is the impedance of the motor at starting? Z01. So here like this, right? So as I told you that it is a step down auto transformer, step down auto transformer, step down auto transformer, the K value will be less than 1. K value will be less than 1, right? So let me consider I'm applying a per phase voltage of V here, V here. If I neglect the primary impedance drop, then E1 is equal to V there, right? And you know that in case of transformers, E2 by E1 is equal to K and E2 is equal to K times of E1. So what is the secondary voltage means? It is K times of E1, nothing but K times of V. So what is the voltage we are applying here means we are applying a voltage of KB. So as K is less than 1, then the applied voltage to the stator windings will be less than the rated value. Is this point clear? Confirming? Right, done. Done. Now let me calculate the starting currents. The starting current drawn by the motor, and I'll be finding out the starting current drawn from the supply. Then what is the starting current drawn by the motor? You can see the starting current drawn by the motor will be the applied voltage. What is that voltage? KB by the impedance Z01. And you know that K into V by Z01. So it is K times ISC. So already I told you that ISC is nothing but the current with rated voltage. So it is K times that current. Now let me find out the starting torque to full load torque. Starting torque to full load torque. What is the equation we are having? It is the starting current by the full load current into whole square into SFL. But here the starting current will be K times the short circuit current. If that is the case, if I simplify all these things, I'll get the starting torque with auto transformer is equal to K squared times ISC by IFL whole square into SFL into TFL. This is K square into the starting torque with DOL starting. Why? Because ISC by IFL whole square into SFL into TFL is nothing but the starting torque with DOL. So what is that first observation? The starting torque with auto transformer. AT means auto transformer is K square times the starting torque with DOL status. DOL status. DOL status. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. Right. The next one is, if you look into this current, we have compared the current drawn from the supply. Why? Because which current is going to affect the equipments which are connected across means that current. Why? Because of the drops in the service line, the equipments which are connected will see the low voltages. So which current we need to consider means the current drawn from the supply. In cases, the current drawn from the supply and current drawn by the motor both are same. But whereas in case of this auto transformer starting, the current drawn from the supply, the current drawn by the motor, both are not same. Why? The current drawn from the supply is the primary current. You can see here, this is I1, and the current drawn by the motor is the secondary current I2. And we have a relation between I1 and I2. So I1 by I2, you know that in case of transformers, it is K. If that is the case, I1 is equal to K into I2. So I1 is nothing but the starting current drawn from the supply by an auto transformer is equal to K times I2 is the starting current drawn by the motor. So that is K into what is the starting current drawn by the motor? It is K into ISC again. So K into ISC. So it is how much? It is K square into ISC. ISC, you know, it is a current with rated voltage. So finally, you can see all these equations. The starting current drawn from the supply by an auto transformer is K square times the starting current drawn from the supply by a DOL starter. You can see the current is also reduced by K square times. This is with respect to the current drawn from the supply. You can see how much percentage the current is reduced from the supply. It is K square time. Torque is also reduced by K square times. Let me fill that column here. The other starter is auto transformer starter, right? So the starting current drawn from the supply by auto transformer is equal to K square times the starting current drawn from the supply by a DOL. The starting torque with auto transformer is equal to K square times the starting torque with DOL. Is it clear? Confirm me all of you. Confirm me all of you. Right. Now what I will do means, not now what I will do means, I'll take this motor, this motor, this motor. This motor is initially started with rated voltage at rated frequency. So the currents are 100 amperes and 100 Newton meters. Now let us consider if the same motor is started with an auto transformer, with K is equal to some 0.945. So can you please tell me what is root of 0.9? Can you please tell me what is root of 0.9? Root of 0.9. 9486. So 9486, right? So here, this time what I'm trying to do means I'm trying to start this motor with K is equal to 0.9486. With K is equal to 0.9486, whereas K square will be 0.9. Then what will be the currents? 90, and what will be the torque? 90. So the question will be like this, Papa. What is that question? A three-phase induction motor is initially started with rated voltage at rated frequency. It is drawing a current of 100 amperes and developing a torque of 100 Newton meters. If the same motor is started with an auto transformer with K is equal to 0.9486, what will be the current drawn and what will be the torque compared to the direct rated voltage? So the answer will be 90 amperes and the torque will be 90 Newton meters. I hope this point is clear. Confirm me. Confirm me all of you. Right. So here the good thing is you can see when compared to a variable reactor starter. In case of variable reactor starter, you can see for 90 amperes current, what is the torque developed? 81 Newton meters. But you can see for the same 90 amperes, what is the torque developed here? 90 Newton meters. So when compared to a variable reactor starter, this starter, auto transformer starter can give better torque or high torque. So that is the reason we use these auto transformer starters for high starting torque loads. That means when you are having some load on an induction motor, and if you are going to start the motor with load, then comparatively you need high torque. So in that case, which starters we are trying to use means auto transformer starters. So these auto transformer starters are used when there is a load on the motor. When there is a load on the motor, the torque requirement is more, and hence the auto transformer can provide a better torque compared to a variable reactor starter. I hope this point is clear. Confirm me all of you. Right. But what is the main problem we are having with a auto transformer starters means the cost will be very high. It is a high cost. So what is the meaning of that? If I'm considering a 10 HP motor, say the cost of 10 HP motor is some 20,000. Let me assume 20,000. The cost of a starter for the 20,000 motor will be nearly 40,000. So compared to a motor cost, the starter cost will be very high. So for that reason, we don't use this auto transformer for all types of motors. We use for high HP motors greater than 20 HP. Why? Because the torque requirements will be more compared to the motor cost. The auto transformer cost will be less in that case. Is it clear? Confirm me. Confirm me, all of you. Confirm me. Right. Done. So this is something about your auto transformer starters. Next one is star delta starters. Next one is star delta starters, the last starters. Star delta starters. Star delta starters. So remember, these star delta starters we use for delta connected stator windings. Delta connected stator windings. Delta connected stator windings. Stator windings. Now the question comes, why the windings are supposed to be connected in delta, right? If you see the electromagnetic torque, it is directly proportional to V square. Don't ask how. Many times you have seen that relation. The electromagnetic torque is directly proportional to V square per phase square. In case of delta winding, in case of delta connected, the per phase voltages and line voltages are same. What do you mean by that? See, I am having a three-phase winding, right? And I am having a three-phase voltage. How much? 400 volts. If these three-phase windings are connected in star, then the per phase voltage will be 400 by root 3. And if the same three-phase windings are connected in delta, then the per phase voltage will be 400 volts. So in which case the per phase voltage will be more, means in case of delta connection. If the per phase voltages are more, then the running torques will be more. So that is the reason we generally connect the windings when the running torque requirements are more. Why? Because with a star connection, the per phase voltages will be less and hence the running torques will be less. If the windings are connected in delta, the per phase voltages will be same as the line voltages and hence the running torques will be more. So that is the reason we connect the windings in delta. Why? Because if you want to have a good running torques, good running characteristics. Is this point clear? Confirm me. Confirm me. Confirm me. Yes. But unfortunately, what is the problem we are having with this delta connected is running condition. The machine can have a better characteristics. But if you are going to start the motor directly with the delta, if you are going to start the motor directly with the delta, what is the per phase voltage? It is 400 volts. If the per phase voltage is 400 volts, as there is no back EMF, as there is no load impedance, the currents will be very, very, very high. Because of this high currents, the windings will get damaged. Right, the windings will be get damaged. So what is the solution for this means? So your intention is to design the stator windings with the delta connection for good running characteristics. But if the windings are connected in delta during starting also, the windings will get definitely damages. So what is the solution for that means? See, you don't start the motor directly with the delta, you start the motor with a star. If you are going to start the motor with a star compared to delta, the currents will be less. Once the motor picks up the speed, then you can reconnect the windings in delta so that the per phase voltages are equal to line and the running characteristics will be good. Running torques will be good. I hope this is clear. Confirm me all of you. Confirm me all of you. Right. So what I will try to do now means first I will pre-assume that the windings are connected in delta and started. If the windings are connected in delta and started, we'll see what will be the currents and we'll see what will be the torques. After that, if the windings are connected in star and started, we'll see the currents and torque and we'll compare in which case the currents will be less and how much it will be less, right? Let us see. Let us see. Let us see. First, let us assume the windings are connected in delta and started. It is direct online. That means with a direct delta, the machine is started. Direct online. Direct online. It is with a direct delta we have connected. See. So the windings are connected in delta. And started. Started. Let us consider we are applying a voltage of V. So here V is a phase line voltage. Please remember it is a line voltage. Please. So here it is Z01. Here it is Z01. Here it is Z01. So in case of delta, the line voltages and phase voltages both are same. Then what is the starting current drawn per phase here? Per phase, I'll find out. The starting current per phase is equal to V by Z01. Is it clear? Confirm me, all of you. Raise the hands. Raise the hands. Right. Then here what will be the line currents? The starting current drawn from the supply with the delta connection. So the starting current drawn from the supply with a delta connection is nothing but the root 3 times the phase current. Root 3 times the phase current. I hope it is also clear. Confirm me once. Confirm me once, all of you. Right. Done. Then I want to calculate the starting torque. Starting torque is directly proportional to per phase square. So the starting torque with a delta is equal to the proportionality constant. I'll take it as some alpha. What is that per phase voltage? It is V square. Directly it is V square. So these are the values when the windings are connected in delta and started. Is it clear? Confirm me, all of you. Confirm me, all of you. Right. So my first half is, instead of connecting in star, if I'm going to connect the motor in delta, what will be the values? We have seen. The next one is, if the windings are connected in delta and star. Sorry. So time is 6:44. Right. Right. Thank you, Baba. Right. I'll stop for 2-3 minutes. I'll come back. Right. Please don't mind. I'll come back. Please. Right. Thank you. I'm back. Right. Right. All of you, can you see the board? Confirm me. I'll proceed. Right. So now, so here the windings are connected in delta as usual, and they have directly started with the delta. Right. So why root 3? See, Baba, why root 3 means, you know that in case of delta connection, the line currents are root 3 times the phase current. That's the reason root 3. I think it is clear. Anonymous attendee. Root 3, right? Please. See, but the anonymous attendee. So this is the only, for today only I'm giving break. From tomorrow, such. Anyhow. Now, second one is, instead of direct delta starting, if the windings are connected in star starting, what happens? Right? Instead of direct delta, if the windings are connected in star unstarted, right? We'll see what will be the equations. Like this. What is the impedance? Z01, Z01, Z01. So what is the voltage we are applying here? V. And you know that in case of star, the per phase voltage will be V by root 3. V by root 3. Is this point clear? Confirm me all of you. Confirm me all of you. Again, low battery. See, I would have connected that. So let me finish this for a while. Then what is the starting current drawn per phase? The starting current drawn per phase will be, just 1 second, I'll finish that. But charging also it is 9%. Otherwise it will go. Right. Charging is done. So what is the starting current per phase? It is V by root 3 into Z01. Is it clear? Confirm me. Is it clear? Confirm me. Raise the hands. Right. And in case of star, the starting current drawn from the supply with the star is same as the phase current. Then what is the starting current drawn from the supply with the star is V by root 3 into Z0. Right? Done. Then what is the starting torque? Starting torque is directly proportional to per phase square. So starting torque with the star is equal to some alpha. What is that per phase square here? V by root 3 whole square is alpha V square by 3. So this is with star connection. Now let us find out the ratio. So starting current drawn from the supply with the star by the starting current drawn from the supply with the delta is equal to V by root 3 into Z01 by root 3 into V by Z01. So this is 1 by 3. So here starting current drawn from the supply with star is equal to 1 by 3 times the starting current drawn from the supply with delta. Similarly, the starting torque with star will be 1 by 3 times the starting torque with delta. These are the equation. Let me once again repeat and revise this. Listen, all of you. So these star delta starters are used when the windings are connected in delta. Now, there is one justification why the stator windings are connected in delta. Why? Because in delta, the per phase voltage magnitudes will be same as the line voltage magnitudes. The running torques will be very good. That is the reason we connect the windings in delta. But what is the main problem is if you are going to start the motor directly with a delta, as the per phase voltages are same as the line voltages, the currents will be very high. So for that, what is the solution is, instead of starting the motor with delta, you start the motor with a star. Then if you are starting the motor with a star, then compared to direct delta starting, the currents will be 1 by 3 and the torques will be 1 by 3. So we are able to control the current to 1 by 3 times the DOL, the direct delta starting, and the torques also 1 by 3 times the direct delta starting. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right? I'll fill this here. I'll fill this here. I'll fill this here. So I'll fill this column here. So the starting current drawn from the supply with the star is equal to 1 by 3 times the starting current drawn from the supply with the delta. The starting torque with the star is equal to 1 by 3 times the starting torque with the delta. So here it is 100 by 3. Here it is 100 by 3. The answer is like this. Now the question comes, how to change star to delta, right? See here in this case, the three-phase stator windings are not permanently connected in star or delta. So those 6 terminals are being brought out. If I'm talking about phase A, the terminals are A dash, B dash, C dash, like 6 terminals are brought out and they are connected at the back of the dabba, star delta starter. There will be a handle, and if you are trying to press that handle down during starting, internally will be joined. That means the windings will be connected in star. After 70 to 80%, then manually you'll throw that handle up. Then the dissimilar events will be connected. Then the windings will be connected in delta. Like that, manually you are changing the stator windings from star during starting to delta. Manually you are trying to change. So like that we can change a star connection to delta connection. But the same thing can be done using a automatic star delta starter. A microcontroller will be there, a coding will be there. Basing on that, the switching will be done from star during starting to delta during running. Like that we can change our star to delta. I think this point is clear. Confirm me, all of you. Confirm me, all of you. Right. So what is a good thing we are having with the star delta starter is, good thing is, see, here the change in current a square times, the change in current is 1 by 3, change in torque is also 1 by 3. Reduction in current, reduction in torque, both are same. The cost is also very less, and hence for all medium range, 5 to 20 HP motors, we use this star delta starters. So there is one very, very important question. A star delta starter is equivalent to an auto transformer with a transformation ratio. That means in place of k square, what is that you are having? 1 by 3. So it is 1 by root 3 times. So can I say a star delta starter is equivalent to a auto transformer with the transformation ratio ratio k is equal to 1 by root 3. Why? Because in place of k square, we are having 1 by 3. K will be 1 by root 3. So this is something about star delta starters. So let me once again revise the starting methods. Once again, please. See, as the name suggests, as the name tells, the purpose of starters for a three-phase induction motor is not for starting the motor. Why? Because a three-phase induction motor is a self-starting motor. But why we need a starter means to limit the high starting currents. Why the starting currents will be high means due to the high relative speed between the magnetic field and the rotor conductors, that is Ns during starting. Flux cuttings will be maximum, EMFs will be maximum, currents will be maximum, and hence the current drawn from the supply will be maximum. And if such high currents are flowing in the windings, definitely due to that high ohmic losses, the temperatures will be raising, the insulation will melt and windings will get damaged. So to limit that, compulsorily we need a starter. So in case of slip ring induction motors, using that additional resistance in the rotor circuit, we can limit such high starting current. But whereas in case of squirrel cage, the only method to reduce that high starting current is starting the motor with reduced voltages. But what is the main problem we are having means the starting torque is directly proportional to the square of the voltage. Whenever you are reducing the voltage, to reduce the starting current, we need to sacrifice some of the starting torque also. So for that, we have seen some relation and we have classified the types of starters like full voltage starting and reduced voltage starting. Like that, we have a comparison. Is it clear? Confirm me, all of you. Raise the hands. Right. The next topic. Next topic. Before I move to the next topic, if anyone questions, what is that you have learned as of now? See, I try to correlate. Why? Because we should know what is that we are learning. After that, we learn that. Please, we correlate. So what is that you have learned means? So before we start construction of an induction machine, we have learned all the basic laws, basic rules. After that, we have learned how to produce a rotating magnetic field, the theoretical proof for that, the conditions for three-phase, M-phase and two-phase. After that, we have learned the construction of an induction machine. In that, we have learned the concept of slots, the concept of torque production, like that everything we have learned with respect to construction. After that, we have learned the working principle. After that, to find out the performance of an induction motor, so we have represented that machine first initially with rotor circuit, then we have calculated the approximate analysis. After that, we have represented the complete circuit. You have represented the, we have calculated the exact values. After that, as this motor will draw high currents during starting, we have seen what is the reason for that. And in order to control such high starting currents, what are the techniques or the starters available? We have seen. This is what we have studied as of now. Confirm me, all of you. Confirm me, all of you. Right. The next topic is, see, I want to control the speed of an induction motor. Speed of an induction motor. I want to use that induction motor for a variable speed, right? In variable speed drive applications, I want to control the speed of an induction motor. But the sad thing is, before the invention of this so-called as power electronic converters, the so-called as SCR and other switching devices, the control of this induction motor was very difficult and it was very complicated. But with the invention of these power electronic devices or these power electronics components, so the control of this induction motor becomes very simple and easy. Now let us see how to control the speed of a induction motor. The next concept is the speed control of an induction motor, right? Let us see. Speed control of a three-phase induction motor. Induction motor. One second. Right. So if I take the basic speed equation, what is the basic speed equation we are having? basic speed equation. Basic speed equation nr is equal to ns into 1 minus s. By looking this equation, one can say that the speed of an induction motor can be controlled by controlling two parameters. What are those two parameters? One is the synchronous speed, the other one is the slip. These are the only two parameters by which we can control the speed of a induction motor, right? Now let us see what is the relation we have between the rotor speed and the synchronous speed. So Nr is directly proportional to Ns when I'm keeping that slip constant. So by some means or by somehow, if I'm increasing the synchronous speed, the rotor speed will be increased. By some means or by somehow, if I'm decreasing the synchronous speed, the rotor speed will be decreased. So what is the relation we are having between the rotor speed and the synchronous speed? Means they are directly proportional to each other. Similarly, what is the relation we are having between the rotor speed and the slip? Means inversely proportional. Inversely doesn't mean that they hold direct relation like inverse. Inversely. What is the meaning of inversely? Means inversely proportional to slip. What is the meaning of that? Please see. If I am considering a 6-pole motor, say the supply frequency is 50 Hertz. Then what is the value of Ns in this? It is 1000 RPM. 1000 RPM. Let the slip is say 0.1. Let the slip is say 0.1. Then what is the rotor speed? It is 1000 into 1 minus 0.1. So it is 900 RPM. Now I'm increasing the slip to say 0.2. I'm increasing the slip to 0.2. Then what is the rotor speed we are having? 1000 into 1 minus 0.2. So it is 800 RPM. So what is the relation we are having? With the increase in slip, the speed of the motor is decreasing, right? So finally, can I say, if you want to control the speed of a three-phase induction motor, so you can control the speed either by varying the synchronous speed, the field speed, or by varying the slip. So these are the two parameters by which we can control the speed of a three-phase induction motor. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So now instead of explaining the speed control by a synchronous speed control or by a slip, so what I'll try to means, I'll try to categorize the speed control into two parts. One is the speed control from stator side, the speed control from rotor side. We will see what are the parameters available in the stator to vary the speed, what are the parameters available in the rotor to vary the speed. So whenever we are talking about the speed control from the rotor side, please remember those techniques are applicable only for slip ring induction motors. Why? Because the rotor circuit parameters can be varied only in case of slip ring induction motor, right? So let us see the control from stator side, control from stator, rotor side, control from stator side, control from stator side. So in this, the first one is the voltage control. Second one is pole changing. Third one is frequency control. Frequency control. These are the parameters by which we can control the speed of an induction motor from stator side, right? These are the controls from stator side. Next is control from rotor side. Control from rotor side. So whenever I'm talking about the rotor side control techniques, please remember that they are applicable only for slip ring induction motor. So these techniques are available for slip ring induction motor. Or these are applicable only for, not available, let us write applicable for slip ring. Slip ring. So what are those in that? First one is in this rotor resistance, rotor resistance control. Second one is by injecting EMF. Third one is cascade connection. Cascade connection, right? So these are the techniques available for rotor side control. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. But when I'm talking about the stator side control techniques, you can see that we can control the speed of an induction motor by varying the supply voltage. But if you look into this basic equation, there is no like voltage term. There is no like voltage term. Then how can I say that the speed of an induction motor can be controlled by varying the supply voltage? Means I'll take one more equation. What is that one more equation? C. So what are the two equations I'll be using in the speed control? Means first one is the basic speed equation, NR is equal to NS into 1 minus S. The other one is the torque equation. It is 180 by 2 pi NS into S V square by R2. So these are the two equations which I'll be using to explain all the speed control techniques, right? So first I'll take a numerical, then we'll go for a break. What is that? C. We have an induction motor which we have designed. This is the induction motor which we have designed. What are the rotor circuit parameters? The rotor circuit parameters are R2 is equal to 0.1 ohm, X2 naught is equal to 0.85 ohms. The number of poles are 6. The stator windings are connected in star. Stator to rotor turns ratio is A. Now this motor, when I'm exciting with a 400 volts, 50 hertz supply, it is operating with a speed of, or it is rotating with a speed of 950 rpm and at a slip of 0.05, 1000 minus 950 by 1000, 0.95, and it is 0.05, and it is driving a constant torque load. What do you mean by that? See, let me assume the speed of the lift is something like 950 rpm. It may not be, just I'm talking with respect to motor side. 950 rpm, right? So it is driving a constant torque load. Now our aim is, our target is to vary either the stator side parameters, or you vary the rotor side parameters. See that how we can vary this speed. You tell me how to vary that speed. You vary either the stator side parameters, you vary the rotor side parameters. You tell me how to vary the speed from 950 to other values. Our intention is to control the 950 rpm speed. Now let us see what are the parameters available in the stator side to vary the speed. What are the parameters available in the rotor to vary the speed? I think our target is clear. Confirm me all of you. Confirm me all of you. Right. I think in your previous machines, DC machines, you might have learned. If not, you are going to learn. So while you are controlling the speed, the motor may behave in two modes. The constant torque mode, when you are controlling the speeds below rated, and it will be operating in constant power mode when you are controlling the speed above rated. What is that? We'll see here also, don't worry. So this is something about your speed control technique introduction. So we'll start with voltage control after the break. I hope this point is clear. Confirm me all of you. Confirm me. right? Please, this speed control technique is one more very important concept in induction motor. Many times in interviews, there were questions from this speed control techniques. In exams, we have questions from the speed control techniques. Please remember, be patient and try to attend, right? Why? Because what I observed after this break, some 10-15 students, they are leaving the class. Don't do that. Please try to be here. I'll come back, right? After the break, I'll join. Thank you. Right, I'm back. Right. So all of you, can you see the video, audio, and the board? Confirm me once. Right. So now we are trying to talk about voltage control. Please see how by varying the supply voltage, we can control the speed of the motor. Voltage control. Voltage control, right? Please. Control. See, when I'm talking about the voltage control, that means by varying the magnitude of the supply voltage, we are going to control the speed. So when we are varying the magnitude of the supply voltage, the other parameters are kept constant. We are not changing either the supply frequency or any motor parameters we are going to change. All those parameters are kept constant, right? See, here only we are varying voltage magnitude, supply voltage, frequency of that is kept constant, motor poles are kept constant, resistance is kept constant, x2 naught is kept constant, and the other parameters are kept constant. Other parameters are kept constant. Only we are varying the voltage. So here, if I take this electromagnetic torque equation, electromagnetic torque is 180 by 2 pi ns s v square by r. Here you can see we are not changing either poles or frequency. If we are not changing the poles and frequency, then obviously the synchronous speed will remain constant. Why? Because 120 into f by p, as we are not changing poles and frequency, the synchronous speed will be constant, and this will be constant. And we are not changing the resistance is also constant. Then you can see the motor torque is directly proportional to into S into V square, right? Is it clear? Confirm me, all of you. Is it clear? Confirm me, all of you. Right. Then what is the load the motor is driving? The motor is driving a constant torque load. The motor is driving a constant torque load. So the magnitude of the torque will always remain constant. Then you know that for stable operation, the motor torque and the load torque should be same. As the load torque is constant, to supply that same torque, the motor torque also should remain constant. For that, S into V square should remain constant. Once again, I'll repeat. So what is the load the motor is driving now? The motor is driving a constant torque load. That means the load on the motor is always constant. And you know that for stable operation, the motor torque and the load torque should remain same. When the load torque is constant, the motor torque also should remain constant for every speed. So if the motor torque has to remain constant, then S into V square should remain constant. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Raise the hands. If that is the case, slip is inversely proportional to voltage square. So if I keep the supply frequency constant, if I'm decreasing the voltage, the slip increases. As slip increases, you know that NR is equal to NS into 1 minus S. When slip increases, the speed of the motor decreases. Like that, we can control the speed of the motor. So I'll take one numerical. From that, you can understand in a better way how by varying the supply voltage magnitude, we can control the speed, right? We'll see that. See, what are the initial voltages? You can see, I told you this is the example which I'm taking. So what is the initial voltage we are having? V1 is equal to 400 volts and F1 is equal to how much? 50 hertz. What is the value of NS1? NS1 is equal to 120 into 50 by 6, 1000 RPM, right? So these are the initial values. Now I'm reducing the voltage to 300 volts. I'm reducing the voltage to 300 volts, keeping all other parameters constant. So frequency I'm not changing, frequency same 50 hertz, poles I'm not changing, same 6 poles, then NS will be how much? 1000 RPM only. So NS2 is also 1000 RPM. I need to calculate NR2. NR2 is equal to NS2 into 1 minus S2. So what is unknown here? S2. So here S into V square is constant. So from this S1 V1 square is equal to S2 V2 square. So from this 0.05 into V1 is 400 square is equal to how much into the voltage is reduced to 300. So from this the value of S2 is 0.088. If it is the case, the rotor speed NR2 will be equal to 1000 into 1 minus 0.088. If this is the case, the speed will be 912 RPM approximately. So this is the speed, right? So the question will be asked like this. The question will be asked like this. A three-phase 400 volts, 50 hertz, 6-pole induction motor is operating at a speed of 950 RPM and driving a constant torque load. Driving a constant torque load. The speed of the motor is controlled by varying the supply voltage. What is the speed of the motor if the input voltage is reduced to 300 volts? What is the answer for this? 912 RPM. So can I say when the voltage is 400, the speed of the motor is 950. When we are reducing the voltage to 300 volts, the speed of the motor is reduced to 912 RPM. So if anyone questions you, there is no like voltage term in speed equation. There is no like voltage term in the speed equation. You can see there is no voltage term in the speed equation. But how can you say that by varying the magnitude of voltage, you can vary the speed means? So by varying the magnitude of the voltage, we are varying the slip of that motor. When we are varying the slip of the motor, the speed of the motor can be varied. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So here you are supposed to note one point. What is that? Whenever we are talking about a speed control, compulsorily the load information has to be given. Without the load information, it is not possible to calculate the speed. For example, in this case, instead of driving a constant torque load, the motor is driving a fan load. In that case, you cannot use these equations. Why? Because in case of fan load, the torque relation is different. So I give the equations for fan load in this particular case, but for the remaining speed control techniques, I take only the constant torque. Why I'm taking a fan load here means just to tell whenever we are talking about the speed control technique, which information is must means the load information is must. Without load information, it is not possible to calculate the speed, right? For example, in this case, instead of using the motor in lift application, say the three-phase induction motor is used in fan application. Then if I'm trying to reduce the speed, if I'm trying to reduce the voltage to 300 volts, then what will be the speed we are trying to see? For example, for example, for example, instead of instead of a constant torque load, if the motor is driving a fan load. A fan load. What happened? Fan load. What happened? Let us see. So you know that in case of fan load, the load torque is directly proportional to N square, directly proportional to Ns into 1 minus S whole square. So here the frequency controls are constant, Ns will remain constant, then the load torque is directly proportional to 1 minus S whole square. Then the motor torque also is directly proportional to same 1 minus S whole square. Why? Because for stable operation, both the torque should be same. Then I'll relate this with this. So here, it should not be constant. So S into V square should be directly proportional to 1 minus S whole square. From this, S1 V1 square by 1 minus S1 square is equal to S2 V2 square by 1 minus S2 square. From that, you need to calculate S2, and from that you need to calculate NR2 is equal to NS2 into 1 minus S2. Like that we can control the speed if the motor is driving a fan load, right? So very compulsorily, which information is must while we are talking about the speed control means compulsorily the load information is a must. When the load information is not given, then you have to assume that the motor is driving a constant torque load, and using that you have to go for that. I hope this point is clear. Confirm me, all of you. Confirm me. Right. So can I write a note? So here, which information is must? Load information is must. Load information is must. Load information is must. Must. Right. So here I have given for one more load, that is fan load. But for the other speed control techniques, I consider only a constant torque load. It is enough. According to your syllabus, it is enough. We discuss only for constant torque load, right? So once again, let me go back. So here our intention is to control the speed. Which speed I need to control? This 90 RPM I need to control. So now we are going to control that speed by varying the supply voltage magnitude. And we are keeping all other parameters constant. If you look into this, as we are varying only the supply voltage magnitude, then the electromagnetic torque is directly proportional to S into V square. So what is the load it is driving now? Means it is driving a constant torque load. Then the motor torque has to remain constant. For that, S into V square should remain constant, right? Then what is the relation we are having? S is inversely proportional to V square. So keeping the supply frequency constant, if you are reducing the voltage, the slip increases to maintain the torque constant. When slip increases, then obviously what happened to the speed of the motor decreases. Right? So can I say like this? In this method, in this method, in this method, keeping the supply frequency constant, the input voltage magnitude is reduced, reduced, right? Reduce. When input voltage magnitude is reduced, the slip increases, the slip increases to keep torque constant. Why? Because the load is constant, torque constant. As slip increases, the speed of the motor motor decreases. I hope this point is clear. Confirm me all of you. Raise the hands. Confirm me all of you. Raise the hands. Right. See, in every speed control techniques, we are having two models. What is that model? First one is the initial voltage is this much, and we are reducing the voltage to this much. Then for that voltage, what is the speed of the motor? That is one mode. The other mode is the speed of the motor is 950 rpm, and I want to reduce the speed by 10%. So in that 950, I want to reduce the speed by 10%. Then in that case, what is the voltage I need to apply, right? The reverse question, right? Let us see how many will answer to this question. For the above problem, the common data. For the above problem, calculate the voltage required to reduce the speed by 10% when the motor is driving a constant torque load. Do it. I'll give some time. Do it. I'm waiting. Do it. I'm waiting. Give the answer. 234 volts. Imtiaz Pasha. Excellent. See, for the above problem, Vikrant, this problem. So what is the initial speed? 950, and I want to reduce the speed by 10% in that. Then what is the voltage required? Vikrant. So one student has given the answer. It is 234. The other anonymous attendee 232, very close to 234. We'll see what is the answer for that. Don't worry. $234.8, Sajjan Singh. 234.8, Chelluri Sarath. Yeah, enough. So it is 234 is absolutely correct. Enough. Please don't give the answer. It is enough. See, here I want to reduce the speed by 10%. Then I'm doing the answer for C. So here NR2 should be 10% less. So 950 minus 10% of that into 950. So it is 855 RPM. I want to reduce the speed from 950 RPM to 855 RPM. Then what will be the slip? As we are not changing the frequency and poles, the synchronous speed will be same by 1000. So it is 0.145. So here the motor is driving which load here? Constant torque load. So S into V square should remain constant. So here S1 into V1 square is equal to S2 into V2 square. So I need to know what is the value of V2. So V2 is equal to, so it is S1 by S2 under root into V1. So it is what the value of S1 0.05 by 0.145 into what the value of V1 is 400. If I simplify this, roughly it is 234 volts. So this is the voltage what you need to apply to reduce the speed by 10%. I hope this is clear. All of you confirm with me. Confirm with me. Right. So now this is clear. So with respect to equation wise, I can say whenever you are decreasing the voltage, the speed of the motor is decreased. But what is the mechanism that is happening inside? So whenever you are decreasing the speed, why? Whenever you are decreasing the voltage, why the speed of the motor is reduced? Let us see. I'll explain this with the help of a torque slip characteristics. Please see here. Please see here, all of you. So this is the electromagnetic torque in Newton meters, and this is the slip. So let me draw for rated voltage first. This is for rated voltage. Let me draw. This is for some voltage V1 at a frequency of F1 or F. Then I'm reducing the voltage. When I'm reducing the voltage, you know that the maximum torque decreases and also the starting torque decreases. Don't ask how, already we have seen. This is with a voltage. Then I'll draw another voltage V3. This is V3. So these are the family of torque slip characteristics with the different voltages. Is this clear? Confirm. Is this characteristics clear? Confirm. So here V3 is less than V2, less than V1, right? Now here the motor is driving which load here? The motor is driving a constant torque load. Let me draw the constant torque load. The motor is driving a constant torque load. The motor is driving a constant torque load. This is the load torque, right? Is it clear? Confirm, all of you. Is it clear? Confirm, all of you. Right. So here, please see. I'll zoom this. See here. When the voltage is 400 volts, when the voltage is 400 volts, when the voltage is 400 volts, so this is the operating point. Electromagnetic torque is equal to load torque. Then this is the speed at which the motor is operating. What is the speed at which the motor is operating? It is operating with a 950 RPM. 950 RPM. Why? Because at 950 RPM with 400 volts, the motor torque and the load torque both are same. Is it clear? Confirm me. Is it clear? Confirm me. Right. So what I'm trying to means, I'll take the torque equation. It is 180 by 2 pi ns S V square by R2. Then what I'm trying to do means keeping that supply frequency constant, I'm decreasing the voltage. When I'm decreasing the voltage, very immediately what happened to the motor torque value decreases. So the motor torque will fall from here to here. Here. Then you can see with the 300 volts, with the 300 volts at 950 RPM, both torques are not same. You can see the motor torque value is decrease. Motor torque value is decrease. So at 950 RPM, motor torque and load torque both are not same. Is it clear? So when the voltage is 300 at 950 RPM, both the torques are not same. Which torque is less? The motor torque is less than the load torque. Is it clear? Confirm me. Confirm me. Confirm me. So when both the torques are not same, then that whatever the speed the motor have, that is not a steady state speed. The motor cannot continue to run with that speed. So here, which torque is reduced now? The motor torque. So which torque is dominating here? The load torque. As the load torque is dominating, as the weight on the head is more compared to the energy, then the rotor has to slow down. So from 950 RPM, the motor will slow down here. It is slow down here. When the motor is slowing down here, you can see the torque value is increasing here. When it is slowing down, the torque value is increasing like this, increasing like this, increasing like this. So again at a particular speed, in this case at NR2, in this case 912 RPM, both the torques are becoming same. Again here the motor is finding that the load torque and the motor torque both are same. As a result, the motor will continue to rotate with a speed of 912 RPM. So can I say When the input voltage is 300 volts, then at 912 RPM, both the torques are becoming same, right? Please. Right, done. Sorry. So at 912 RPM with 300 volts, both the torques are same. So can I say like this? So whenever you are decreasing the voltage, whenever you are decreasing the voltage, immediately the motor torque is decreasing. Motor torque is decreasing. When the motor torque is decreasing, the speed is decreasing. When the speed is decreasing, again what happened to the slip? Increases. When the slip increases, again what happened to this motor torque? Increases. So these two torques will cancel out, and finally the motor will operate with a new speed. So can I say, whatever the reduction we have in the motor torque, whatever the reduction we have in the motor torque, due to the reduction in voltage, that is been compensated by increase in motor torque due to the increase in slip. So this will be cancelling out and this will remain constant. As slip increases, what happened to the speed? Decreases. So can I say like this? Keeping the supply frequency constant, if the input voltage is reduced, the slip increases. Keeping the supply frequency constant, if the input voltage is reduced, the slip increases to maintain the torque constant. As slip increases, the speed of the motor decreases. Like this, if I'm going to decrease the voltage still further, then it will fall on this and it will deaccelerate and the torque will be again somewhere here. So it will operate with a speed of NR3. Is this point clear? Confirming? Is this point clear? Confirm, all of you? Right. So if anyone questions you, whenever you are decreasing the voltage, why the torque, why the speed is decreasing means, so indirectly by decreasing the voltage, you are making that motor torque to decrease. When the motor torque is made to decrease, then as the load is dominating, the motor will decelerate, the motor will slow down. When the motor is slowing down, again the torque is increasing at a new speed, both the torques are becoming same and the motor will continue to rotate with that particular speed. I think this point is clear. Confirm me all of you. Confirm me all of you. So this is something about your voltage control. Voltage control, right? Now let's see the drawbacks of this voltage control. Drawbacks of this voltage control. What are the drawbacks? What are the drawbacks? Drawbacks. The first drawback is this is applicable only for the speeds below rated. Why? Because if you look into this, right? If you look into this equation says that if the input voltage is increased, then obviously the slip decreases. When the slip decreases, the speed of the motor will increases. This equation says that when you are increasing the input voltage, the slip decreases. When the slip decreases, the speed of the motor will increase. But fortunately or unfortunately, we are not supposed to increase the voltage beyond its rated value. Why? Because if you are increasing the voltage beyond its rated value, that insulation will get damaged, the windings will get damaged. So even though the equation says that we can increase the voltage to increase the speed, it is not practically possible. So for that, always we can reduce the voltage and always we can reduce the speed. So using this, we can control the speeds below rated, but not above rated. Why? Because for above rated, we need to increase the voltage, which is not practically possible. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So speeds below rated are possible. Speeds below rated are possible. Below rated are possible. Below rated are possible. Second point is, please see here. So here, by reducing that voltage, we are decreasing the speed. When we are decreasing the speed, the relative speed between field and conductors will increase. Because NS is fixed, right? In the first case, NS is 1000. the speed is 950. In the second case, ns is 1000, the speed is 912. You can see when the speed is reduced from 950 to 912, the relative speed has increased. When the relative speed has increased, then the motor will draw because of the more relative speed, flux cuttings will be more, currents will be more, the motor will draw very high currents. So if this high current flows for long time, what happens to the ohmic losses increases, temperature will increase, and windings will get damaged. Right? So can I say, whenever you are trying to reduce the voltage, the motor will decrease. Right? Whenever you are decreasing the voltage, the speed is decreasing. When speed is decreasing, the relative speed is increasing. Flux cuttings are increasing, currents are increasing, then the ohmic losses will increase. And if such currents, if ohmic losses are more, the windings will get damaged. So this method we cannot use for long time. Why? Because as the ohmic losses are more, there is a possibility that the windings will get damaged. So these are applicable only for short time, but not for long time. I hope this point is clear. Confirm me, all of you. So in cut short, if I want to tell, if I want to tell, S is inversely proportional to voltage square. As you are decreasing the voltage, the slip is increased. And you know that for low slip operation, rotor current is directly proportional to slip. So whenever the slip increases, this I2 increases. When I2 increases, the current drawn from the source will also increases. Then with reduced voltage, the motor will draw high currents. And because of these high currents, the ohmic losses will increase. And if these ohmic losses are there for longer time, then the windings will get damaged. And hence it is applicable only for short time, only for limited time. So here motor draws high currents with reduced voltage. Hence, ohmic losses will be more. Therefore, it is applicable for short time duration, not for long time duration. Is this point clear? Confirm me. Is this point clear? Confirm me, all of you. Right. Third is, so here as frequency and poles are fixed, we are not changing that. Ns is constant. So, right? As frequency and poles are constant, Ns will be constant. And keeping this Ns, if you are taking the rotor speed away by decreasing the voltage, then this relative speed is increasing, flux cuttings are increasing, windings will be damaged. So for that, we cannot take this rotor away from the synchronous speed. So the rotor speed should be very close to synchronous speed. So for that, a wide range of speed controls are not possible. Only the speeds closer to NS are possible. So wide range is not possible. So if wide range means the rotor speed will be away from synchronous, then the windings will get damaged very soon. Wide range is not possible. Only narrow range is possible. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me, all of you. Right. So this is something about voltage control. Note, this is a slip control. This is a slip control. That means using a slip, you are controlling the speed. Second one is, this method is applicable to both squirrel cage induction motors and slip ring induction motors, right? So this is something about voltage control technique. Is it clear? Confirm me, all of you. Is it clear? Confirm me, all of you. Right. This is something about voltage control. The next one is pole changing method. Pole changing method. See, one of the student was asking about this pole changing during my initial classes. I told you that yes, we can change the speed of the motor by changing the poles, right? Let us see how to change the speed of the motor by changing the poles. Let us see. So if you look into this speed equation, NR, it is S into 1 minus S. So this is 120 into F by P into 1 minus S. So from this, I can say NR is inversely proportional to poles, right? See, if I'm decreasing the poles, the synchronous speed will increase, thereby the rotor speed will also increases. If I'm increasing the poles, the synchronous speed will decrease, thereby the rotor speed will also decreases. So what is the relation we are having between the rotor speed and poles means inversely proportional. Is this point clear? Is this point clear? Confirm me. Right. Now the question comes. The design of pole is a design parameter. What is the meaning of design parameters? Design of pole is a parameter. What is the meaning of a design parameter? So these pole design should be done during the construction. Once a motor is ready, once the design is ready, right, it is not possible to change the poles. For example, if anyone asks, I am having an induction motor, can we change the poles during running condition? No, it is not possible. Why? Because you have to wound the coils according to your number of poles. So it is not possible, right? So if anyone questions you in general, is it possible to change the stator poles or the motor poles during dynamic conditions or when the rotor is rotating? Your answer should be no, right? But the thing is, if you want to control the speed of an induction motor by changing this pole changing method, then in that particular case, in that special case, the stator has to be designed, the stator has to be constructed specially and separately. What is that? We'll see. Once again, this equation says that NR is inversely proportional to the number of motor poles. If we are varying the motor poles, the rotor speed will vary. It is clear, absolutely no doubt. Now the question comes, how to change the motor poles when the motor is rotating, when the motor is operating? It is not possible. Why? Because they are the design parameters, they are fixed inside, they cannot be changed during running condition. But if your intention is you are having a three-phase induction motor and you want to change the speed of the three-phase induction motor by changing the poles. So your intention is to change the speed by changing the poles. In that particular case, in that special case, your stator design should be separate, the stator design should be new. So tomorrow, if anyone questions you, is it possible to change the motor speed by changing the motor poles, means you have to say if the stator construction is different from the general stator construction, it is possible. Then how it is different means see. How it is different means see. If I take any three-phase induction motor, in that there will be one set of three-phase winding. One set of three-phase winding. One set of three-phase winding, correct? Only one set will be there, which is wound for particular pole P. Is this point clear? Is this point clear? Raise the hands. Right. So it is having only one set of three-phase winding which are being designed for a particular pole P. But if you want to control the speed of an induction motor by pole change method, so in that particular case, the stator is separate. In what way it is separate means, in that particular stator, we'll be having a pair of two sets of three-phase winding. So here one set is wound for say, so this set is first set of three-phase is wound for say P1 is equal to 6 pole. So this is the other set which is wound for say second set which is wound for say P2 is equal to 4 poles, right? So these are the two sets of three-phase winding. So it is a special stator or a general stator? It is a special stator. What is a general stator? The stator will be carrying only one set of three-phase winding, right? I think this is clear. Confirm me all of you. Confirm me all of you. Right. So here what I'll try to do means I'll try to take a three-phase supply. I'll try to take a three-phase supply here. Red, yellow, blue. Three-phase supply. And I'll take a TPST switch. TPST switch. TPST switch. This is position 1. This is position 2. So this is a rotor. Right? So what is the TPST switch means? Triple pole single throw, TPST switch, right? So here what I'm trying to do means during starting the excitation is given to a three-phase windings which are being wound for 6 poles. So during starting the excitation is given to the first three-phase winding which is wound for 6 poles. So it is 6 poles. Let me consider that this three-phase excitation is 400 volts 50 hertz. So frequency is how much here? 50 hertz. Then NS is how much here? NS 1000 RPM. Let us consider the rotor speed is 950 RPM and slip is say 0.05. This is when the excitation is given to the first three-phase winding, the first set of three-phase winding. Is it clear? Confirm me. Is it clear? Confirm me. Right. Now during running condition, what I'll do means I'll change that switch from position 1 to position 2. Just I'll break that and make to the other set. I'm giving to 4 pole. Then the supply frequency is same. The synchronous speed will rise to 1500 RPM. Why? Because the poles have decreased. Then the rotor speed will be 1500 into 1 minus 0.05. Why? Because the slip will be same. Why? Because the load torque is constant. Then it is 1425 RPM. We can see from 950 RPM, we are increasing the speed to 1425 RPM. Like this, we can control the speed. So can I say like this? Can I say like this? The rotor speed is inversely proportional to the number of poles. By varying the motor poles, we can vary the rotor speed. But the question is, for a general motor, for a general three-phase induction motor, is it possible to vary the speed by varying the poles? Your answer should be no. Why? Because if you look into any three-phase induction motor stator, it carries only one set of three-phase winding, which is wound for only P poles, only one set of P poles, right? Is it clear? Confirm? Confirm? But if you want to control the speed of an induction motor using this pole changing method, in this particular case, the stator should carry a pair of two sets of three-phase windings which are being wound for different number of poles. In this case, one set is wound for 6 poles and the other set is wound for 4 poles. Depending upon the requirement whether to start the motor with low speeds or high speed, the excitation is given to one pair, then the excitation is shifted to the other pair during running condition. Like that, we can change the speed, right? So can I say in this method of speed control, in this method, the stator carries a pair of three-phase windings, which are wound for different number of poles, right? Depending upon the requirement, the excitation is given to, requirement means low speed or high speed, excitation is given to one pair at starting, the same excitation is shifted to the other set or other page during running. I think this point is clear. Confirm me all of you. Confirm me all of you. Confirm me all of you. Right. Then what are the only few? What about others? Please raise the hands. It is a simple topic. It is not like to be discussed in detail. Simple topic. Drawbacks. So what are the drawbacks? See, drawbacks. The first one is bigger size. Bigger size. 1 second. I'll have a glass of water and come. Just 1 second. Right. So why bigger size? Simple. In order to place the conductors of two three-phase windings, why? Because I need to place the conductors of two three-phase windings. If I want to place the conductors of through two three-phase windings, the stator slots with stator slots heights will be more, the overall size will be more, and cost will be more, right? So that is the reason it is a bigger size. Is this point clear? Confirm me. Confirm me. But what is the beauty or advantage means, see here we can have a wide range of speed control. What is the meaning of wide range means? Say in this case, one pair is wound for 2 poles, other pair is wound for say 10 poles. Let us take instead of 6 and 4, one pair is wound for 2 poles, the other pair is wound for 20 poles. If it is 2 poles, the rotor speed will be nearly 3000 rpm, and when you are changing the excitation from 2 poles to 20 poles, the rotor speed will be nearly 300 rpm. Then you can see you are able to reduce the speed by 1/10. 1/10 you can reduce, right? By changing the proper pole combination, we can get a wide range of speed control, right? So wide range is possible here. Wide range is possible here. Possible here. But the problem is the bigger size. The problem is the bigger size. I hope this point is clear. Confirm me. Confirm me. Right. So if you are like worrying about the bigger size, then you can do one thing. You can go for a smaller size. Smaller size. What is the meaning of smaller size means? Instead of taking two three-phase windings separately, you take only one three-phase winding and try to bring that interconnections up. You try to bring that interconnections. You know that interconnections can be brought up, and by changing that interconnections, we can change a p pole to p by 2 pole machine. So you know that the interconnections has to be brought up. So by changing interconnections, we can change a p pole to p by 2. By changing interconnections, we can change a p pole to p by 2 pole machine. So in this case, half the speeds can be possible. If the initial speed is nearly 1000 rpm, we can get the speeds nearly 500 rpm. Only half the speeds are possible. Beyond that, it is not possible. So you have to compromise among these two. What is that? If you want to have a very wide range of speed control, then you need to take two three-phase windings separately. Then the cost will be more, the size will be more, and everything will be more. Then if you say no, I'm not interested to pay more for cost, but I can adjust if I'm having only speeds half the speeds. Then in that case, the interconnections are supposed to be brought out, And by changing the interconnection, we can change a p poles to p by 2 pole machine, and we can get the speeds half compared to the rated value. Is this point clear? Confirm me, confirm me. So you have to compromise at some point here. You have to compromise where you need to compromise now, right? Done. The second one is, the second one is, it is a two-speed motor. Two-speed motor. What is a two-speed motor? You can see. So from 950 RPM, we can change the speed to 1425 RPM. It is only two speeds. We can get two speeds. Either the motor can run with 950 in this case or 1425. Only two speeds. Only two steps we can have. But I can have four steps. One of the student has given one question. Sir, one of the answer is 600 and other answer is 1200. How, sir? I told him. So you can learn this in speed control techniques. You can just answer to that question. Please see. So two speed motor. Why? Because only two pole. But I can make it four speeds. I can make it four speeds. Four speeds means don't say that you'll be using four winding. No. Here we use one set of three-phase winding. One set. A P pole can be changed into P and P by 2. I'll be using another set of three-phase winding. P2 pole, I can change to P2 and P2 by 2. So how many pole pair combinations I can have? P1, P2, P1 by 2, P2 by 2. How many speeds can be possible? Four speeds. So here again the cost will be more. Why the cost will be more? In that four speed operations, how many three-phase windings are required? Two three-phase windings are required. Again, those interconnections are also be brought out. So by changing those interconnection, we can get four sets of poles. Like that, we can get four speeds we can possible, right? So what is the second problem is we have only two speeds, two step speeds. But I can make it into four steps. But in that case, how many three-phase windings are required? Two three-phase windings are required. Again, the interconnections are supposed to be brought out. So by changing those interconnection, we can get four pole pairs and hence we can have four speeds. But here you need to compromise the size, the cost will be more. Why? Because you are placing two windings. So you need to compromise somewhere. Whether you need to have two different wide speeds is enough. First case, like that you have to compromise. Is it clear? Confirm me. Confirm me. So what is the ratio of those four speeds? Why? Because you know that only even to even combinations are possible. Even to odd or odd to fraction are not possible. So what is that possible speeds, right? Speed ratios. This question was asked in many exams. Speed ratios. So what is that? A 12 pole can be changed into 6 pole or 8 pole can be changed into 4 pole, right? So here 12, 8, descending order, 4, 6, 2, 3, 4, 6, 1, 1.5, 2, 3. So what is the ratios of speed means 1 is to 1.5 is to 2 is to 3. What is the meaning of that? Say if the initial speed of the motor is 500, what is the next speed possible? 750. Next speed is 1000. Next speed is 1500. Like that we can get the speeds in steps. So what are the speed ratios means 1 is to 1.5 is to 2 is to 3. So if the initial speed is say 500, the next will be 750, 1000, 1500. If the initial speed is say 1000, then 1500, 2000 and 3000. Like that we can get four speeds. Is this point clear? Confirm me. Confirm me. Right. So this is something about your pole changing method, right? Before I continue with the points, let me tell. So here, as per our equation, NR is inversely proportional to the number of poles. I can say that by changing the motor poles, we can change the rotor speed. But now the question is it possible to change the motor poles during running condition? Your answer should be no in general. But if your intention is to control the speed of an induction motor by changing the poles, in that case, the stator construction has to be separate and the stator construction has to be special. How it has to be special means we have seen. So instead of using only one three-phase winding, we are using two three-phase windings. Like that, we have done all the theory. Is it clear? Confirm me. Confirm me. All right. So this comes under synchronous speed control. Why? Because by changing the poles, which parameter you are changing? Synchronous speed. Note. It is a synchronous speed control. Synchronous speed control. Right? Second, see, this method is applicable only for squirrel cage induction motor. Why? See, you know that in case of squirrel cage, the rotor poles are induced poles. What is the meaning of induced poles means? See, first you are giving the excitation to 6 poles. Then how many poles will be induced in this 6 poles? When you are changing the excitation to 4 poles, then how many poles will be induced in these 4 poles? So which type of rotor can respond to the changes in the stator poles means squirrel cage. But when we are talking about slip ring, already this was explained. Don't ask any questions in the doubt session. Why? Because this is a old topic, not a new topic, please. But if I'm using a slip ring induction motor, say if I'm using 6 poles, then how many pole rotor is required? 6 poles. But when you are changing the excitation from 6 poles to 4 poles, then obviously what happened? The motor will stop. Why? Because the stator poles will be 4, the rotor poles will be still 6. So if you want to have motoring, then you have to rewound the rotor for 6 pole. What is the mechanism? See, the speed of the motor is say 1000 rpm closer. Then suddenly you have changed the stator poles from 6 to 4. The motor will stop there. Stop there. So you are using in a train, that will just stop. Then what you need to do, you have to take out the motor, you have to take out the rotor, you have to rewound the rotor for again 4 poles, then insert that, then start the motor, then it will start rotating. But no one will call that one as a speed control. Speed control means it should be dynamic. So this method is not applicable for which rotor? A slip ring rotor. Why? Because there the rotor poles are not changing automatically. But in which rotor the poles will be changing automatically means squirrel cage. I hope this point is clear. Confirm me all of you. Confirm all of you. So can I say this method this method is applicable to only squirrel cage induction motor. Induction motor. Because only squirrel cage rotor responds automatically to the stator poles. Stator poles. Is this point clear? Confirm me all of you. Is this point clear? Confirm me. All right. So this is something about your pole change. The next and the last in stator is frequency control. Frequency control. First we'll discuss pure frequency control. Frequency control. Right? Done. So we'll see this tomorrow. Tomorrow means tomorrow is a holiday. Next class. We'll see in the next class, right? So this is something about speed control techniques. Two cases. One is the voltage control. The other one is pole changing method. This one is the frequency control. So tomorrow is a festival. So tomorrow is a holiday. I think you know. So next class will be on, tomorrow is Wednesday, Thursday, right? So still class is not over. Let us go for the doubts. We'll see. Just bring that earphones.
See, one small announcement. So that tomorrow holiday only for that new batch. Why? Because tomorrow is a festival, and for me, right? It is festival for other peoples also if we can celebrate. So, and for other people, the old batches. So I'll be having your F&S class. So you please refer to your link or your online schedule, then follow that online schedule accordingly. But for the new batch, which was started on July 5th, so we'll be having holiday for tomorrow. Again, day after tomorrow, so we'll have the class from 5 as usual. There is no change in that schedule, right? Let us discuss the doubts. See, right? First, before I try to proceed that, sir, how to change the number of poles? See, all these stories regard the number of poles only. How to change, right? Why slip is constant? Why? Because the load is constant. When the load is constant, the rotor current should remain constant. For that, the slip should remain constant. Sir, can we change the poles in decimals? How come it is possible? When I'm talking, the poles cannot be changed in odd. How can you talk in fraction? No, right? It is expensive. Yes. Amit Vikram, how the poles will change automatically in squirrel gauge? Please refer to my previous class. I told you already. Right, thank you. Happy Eid, sir. Thank you. Thank you. Tomorrow is there any faults and stability class? Yes, you follow the schedule. Tomorrow is you are having. How to change the post by changing end connection? Please refer to my previous notes. That was already discussed. Please refer to my old notes. Please. Why we need to control the speed of an induction motor? When you are using in a variable speed drives, for example, if you are using in electric vehicles, then if you want to control the speed, then this is one of the method, right? Please. Right, starter for slip ring is nothing but your resistance. That was already discussed. Right, let us see the question and answers. See, my request, don't ask, sir, how the poles can be changed. Say this was a 1.5 hour class during the construction. Please refer that by changing the interconnection, how to change the stator poles, and why in case of the squirrel gauge, the rotor poles are automatically changed. I explained all these things. Please don't ask such questions now. Why? Because it was already discussed long back. Please don't ask now, please. If it is not discussed, then there is a meaning if you ask. Please, it was already discussed. Please refer to the notes. Yes, Sunil.
Hello, sir.
Ha, Baba, Sunil.
Sir, can you explain once again the speed ratio, sir?
Speed ratio. See, already I told you that only even to even
Yes, sir.
combinations are possible, right?
Huh.
Is it possible to change even to odd or odd to fraction?
No,
Poles?
sir.
No.
No, sir.
So basing on that, I have divided. So minimum is 8 4 can be made into 4. A 12 poles can be made into 6. So you can do it like that. So the speed ratio will be 1 is to 1.5 is to 2 is to 3. So this is the minimum speed. If the minimum speed is 100, then the maximum speed will be 300. Like that we can get the speed ratios. We can cross check that. For example, say,
Okay, sir.
no, say, in this case you are taking one winding for 12 poles, right?
Yes,
And
sir.
another winding for 8
Okay, sir.
poles. So these 12 poles can be changed into 6 poles, and these 4 poles can be changed into 2 poles, right? Then what will be the
Yes, sir.
speeds possible? According to that, you have to find out what is the minimum speed. So if the poles are more, the minimum speed ns is equal to 120 into 50 by 12. So it is 10. What
Yes,
is the
sir.
minimum speed in this case? 500. Then the
500.
next speed will be 750. Next speed will be 1000. Next speed will be 1500. Like that, we'll get in this case. Is it clear?
Okay, sir. Clear, sir.
Understood? Right, right.
Yes, sir. Right.
Right. Where is Sai Charan Reddy? Kumar.
Hello, sir. Good evening, sir.
Baba. Good evening, Baba.
Sir, in voltage control method,
Mm-hmm.
as voltage reduces, relative speed increases. So flux linkages increases, right?
Flux cuttings will increase.
Flux cuttings increases. As
Ye-
voltage is similarly as voltage is reduces, V by F raise also reduces, sir.
But here we are not changing frequency.
Yes, sir. So V by F raise also reduces.
See, V by F ratio also reduces, so flux also reduces. Phi is directly proportional to V by F. So keeping this frequency constant, if you are decreasing the voltage, flux will reduce, correct? When flux
Oh.
reduces, maximum torque is reducing, the starting torque will be reducing, the slips remain same. Yes, what is your question?
There is a flux linkages increases, but here flux is reduces.
Yes, flux linkages, that means out of total flux, that phi r, the flux cuttings will increase here.
Okay.
Understood? The flux cuttings will increase here. That means the number of flux lines which are coming, say, when phi r is equal to some 2 Webers, say 20 flux lines are coming.
Yes,
When
sir.
when a part of the flux is reduced, say they are reduced to 18,
Yes,
right?
sir.
But the number of flux lines cutting will be more here. So previously, say there are 2 flux lines cutting, now there will be 5 flux lines cutting. Even this is reduced, but the number of flux lines cutting, the rotor conductors will increase.
Okay, sir. I need some more clarification.
Yeah,
సార్
you can.
ఇప్పుడు ఒకవేళ 20 వెబ్బర్స్ ఉన్నప్పుడు ఫర్ ఎగ్జాంపుల్ 1300 ఆర్పిఎం లో రోటర్ రొటేట్ అయింది అనుకోండి సార్.
Yes.
If I reduce the flux magnitude to 18 webbers.
Yeah. So we are not supposed to talk with respect to Webers here. See, when we are talking about voltage, let me talk with respect to voltage. That flux content is internal.
అంటే ఒకవేళ సేమ్ స్పీడ్ తో రోటర్ రొటేట్ అయినా ఫ్లక్స్ మాగ్నిట్యూడ్ చేంజ్ చేయడం వల్ల ఏమైనా చేంజ్ ఉంటుందా సార్?
I didn't get you. See, when the total flux lines are reduced, okay.
Relative speed is constant, sir.
Here relative speed is not constant, na?
Here okay, sir. I understand in this application. But in normal issue, ఒకవేళ మన రియల్ స్పీడ్ ఒకవేళ రిలేటివ్ స్పీడ్ కాన్స్టెంట్ గా ఉండి ఫ్లక్స్ యొక్క వాల్యూ మాగ్నిట్యూడ్ దట్ ఈస్ 1.5 టైమ్స్ టు 5m కదా సార్. దా 5m వాల్యూని ఒకవేళ నేను రెడ్యూస్ చేస్తే సో అప్పుడు ఏమైనా E2 లో చేంజెస్ వస్తుందా?
See, first thing is how you are changing that flux without changing the relative speed. First question.
Okay.
So if you are maintaining the relative speed constant, definitely the flux should remain constant.
If by changing the reluctance like that, we can change flux.
When you are changing the reluctance, the magnetizing current and other things will differ. The power factors will differ, but the relative speed cannot be changed.
Relative speed change అవుతుంది అనట్లేదు సార్.
ఇప్పుడు అదేనన్నా. See, you mean to say that keeping the relative speed constant, you are reducing the flux.
If in case ఒకవేళ reduce అయితే what about E2? E2 ఎలా అన్నది?
E2 తగ్గుద్ది కదా. E2 will depends upon the total flux lines and the number of flux lines cutting. So it doesn't depends upon your phi r. It depends upon the total number of flux lines cutting the rotor conductors.
Okay.
Understood?
I understand. So here ఒకవేళ తగ్గినా ఆ relative speed వల్ల తగ్గితే more impact. Increase అయ్యింది impact ఎక్కువ.
Yes.
So that's why we said that E2 increases.
Yes. Understood.
Okay, sir. I understand. Thanks.
Right. 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 Arshad Ali. Arshad Ali.
Hello, sir.
Yeah, please.
Sir, in voltage control method, sir, can you please explain me how speed below rated are possible only? Actually, due to my internet issue, I was unable to hear that.
See, when you are decreasing the voltage, what happened to slip? Increases. Can you see the board?
Yes, sir.
When slip increases, what happened to the speed of the motor? Decreases, correct?
Yes, sir.
Right, that is what we have seen. But if I'm trying to increase the voltage, what happened to the slip?
Decreases.
When slip decreases, what happened to the speed?
Speed, it will increase.
Increase. According to the equation, the speed will increase. But is it possible to operate a motor beyond its rated value?
No, no.
Why? Because that insulation will get
Damage.
that is the reason, even though the theory says that the equation says that we can increase the speed by increasing the voltage, we don't do in practical. Why? Because that insulation will get damaged. Forget about the speed control, the machine itself will get damaged. So for that, it is always advisable to go for the speeds below rated, not for above rated.
Thank you, sir.
Right, Arshada? Right, Vishnu.
Sir, good evening, sir.
Good evening, Baba.
Sir, in this direct online starter, sir.
Okay, direct online starter. You asked.
Sir, here in this case, all these points that were mentioned in the class, that is regarding this leakage inductance and stuff, sir. There is already inbuilt in the rotor, no, sir. I mean, already inbuilt in the motor, and the only advantage from what I have seen is for direct online is like when fault occurs, this thing acts as a protective circuit, like.
That is true. But what I mean to say is, whatever you said is absolutely correct. I mean, I told you that if in a particular induction motor, low HP induction motor, the slots are open. Let us consider.
Okay, sir.
With open slots, the current is say 100 amperes.
Okay, sir.
But instead of open slots, if I am using closed slot, what will be the current? 90 amperes. Why? Because the leakage reactance compared to other slots in closed will be more. This was already discussed, correct?
Yes, sir.
Right. So partially with the closed nature of the slots, we can control the starting current, but not to the extent of less than the rated current. So 100 is dangerous current, even 90 amperes is also dangerous current, but we are able to control part of the current because of that closed slots, part of the current. Is it clear?
Sir. Yes, sir.
But the main thing why we are able to use this direct online for low HP means because of the small rated machine, the rotor diameter will be less, the inertia will be less, the time taken to shoot up will be less. So such high currents will flow only for very short time. That is the reason we are using. That is the main criteria for using DOL. For example, if I'm using this DOL for high HP motor, say, the diameter will be more, then the rotor will slowly raise the speed. Meanwhile, the currents will be very high, the temperatures will increase, the insulation will damage, then the motor has to come back to standstill instead of running. Why? Because the windings are damaged.
Okay, sir.
Vishnu,
So yes, sir. This DOL so only is useful in the case of small HP motors.
That's what I told. Right?
Yes, sir. That you mentioned.
Right.
Sir, and
Right.
one more thing regarding these problems, sir. These problems, what are the major sections that you should look into, sir?
See, problems means, see, I told you, even if you look into the yesterday's engineering service examination, so it is something like on the basics they will ask. They will not go in detail, in depth. So they'll ask on the basic levels. See, whatever the questions, whatever the numericals we are seeing, if you follow the content and the concept, then you can solve any questions. So yesterday when I was in, previous classes when I was explaining about the equivalent circuit, so
Yes,
I told you the logic how to solve.
yes,
Right?
sir.
What is required? Then if you know such complete logics, you can solve any numerical. So please remember, my advice is, see, if you just go through one concept, basing on that concept, you try to solve the numericals. Then you'll be perfect in that concept.
Okay, sir. And sir, regarding this yesterday's problem only, this where we use this R Thevenin with X Thevenin and all. If in case gate exam comes, we can just avoid this and go for that approximate, no, sir.
Yeah, he will mention clearly, right? Why? Because in gate they will not ask you to go for V Thevenin or R Thevenin. That why? Because it is a lengthy thing.
Yes,
why?
sir.
Because maximum time what you can spend is 2 to 3 minutes, right?
Yes, sir.
So V Thevenin, R Thevenin will be something like lengthy one. So in that he'll mention clearly, use approximate. In that case, use V1, R1, X1. Is it clear?
Yes, sir.
Right, right.
Thank you, sir.
Right. Right. Imtiaz Pasha.
Good evening, sir.
Good evening, Baba.
Sir, I have doubt that is small doubt.
Yeah, you can ask big doubt also.
Sir, stator windings are connected in star, no, sir.
Say there is no like specific rule to connect in star, right? I told you that, right? It depends upon the availability of starter, the need of starting torque and other things.
Based
So
on that, we can
yeah.
convert.
Huh.
Sir, one more is there, load, in general load.
Hmm.
Sir, whenever the relative speed is more, at
Hmm.
the time, the flux cutting action will be more
Yes.
and the power consumption will be more, no, sir.
No. See, it depends upon your operating power factor. Say if the motor speed is very closer to NS, right?
Sir, I have just small readings.
Yeah, please read.
For example, rotor speed is 500 RPM
Okay.
and synchronous speed is 1500 RPM. At the time, relative speed is 1000.
Yeah, the relay flux cuttings will be more, EMF will be more, currents will be more, but that current is high inductive current.
Then the power consumption will be more, no, sir?
No, high inductive current, that is. When high inductive current, then the reactive power drawn will be more.
Reactive
Right?
power will be more.
Yeah, so that power, when the reactive power is more, obviously the active power fed to the rotor will be less.
Yes, sir.
Right? When the active power is less, obviously what happened to the torque? Less. But because of those high currents, the ohmic losses will be high, then the temperatures will be very high. The efficiency will be very poor.
Yes. Sir, in our home, we are using fan now, sir.
Yes.
If you put at the first stage, in there are 5 readings, 1, 2, 3, 4, 5.
They are steps.
Steppers. If you put that first step, the fan speed is be low, means rotor speed be low, no, sir.
But you are using a dabba regulator or a small knob.
Small knob.
That is a track voltage
Yes,
regulator. So that voltage regulator will control the voltage fed to the fan. So it is not wasting the power. So by controlling the voltage VRMS, the amount of power drawn from that source is reduced. So we are not, in case of your voltage dabba regulators, the power drawn from the source will be same. But in the regulator, you are wasting a part of the power and the power to the motor is reduced. So the power drawn will remain same, power wastage will be there here, the power fed to the motor will be varied. Like that the speed will be varied in olden days. But nowadays you are using a regulator, AC voltage regulator. So by varying that AC voltage regulator, we are not drawing the same power. The power drawn from the source is varied according to the speed required.
Yes, sir.
You understand this?
Yes, sir, I understand.
Hmm.
In that's one AC regulator is no, sir. If you are supplying 230 volts in starting, the fan speed is low, we can consider that we are reducing the voltage for the reducing the speed. Voltage means first method is no, sir, voltage control method.
Yes, absolutely.
With the help of voltage control method, we can reduce the speed.
Yes.
In first stage.
Correct.
According to that, up to 5 stage, we can control the speed with the help of the voltage, reducing the voltage.
Okay, right.
Then I have dot means in first stage our power will be consumption will be more. In the last stage, power consumption will be less because of the flux cutting action.
No. See, it is not the question of flux cutting action. It is the question of you are controlling the voltage. When you are controlling the voltage, you are controlling the flux. When you are controlling the flux and at the same time you are controlling the flux cutting also. The same thing that other person has asked. So when you are decreasing the voltage, what happened to the slip?
Sir, decreases.
Slip increases.
Yes, sir. Inverse proportional slip.
When slip increases, what happened to your so-called as speed now?
Speed will be decreased.
Why? Because you just look into this. Whenever you are decreasing the voltage, what happened to the motor torque?
Decrease.
When
Increase,
the
sir.
motor torque decreases, how can you say increase?
Sir, T proportional to V, no, sir.
V square.
Yes, sir. Tm is proportional to V square. Means at the time V decreases, yes, sir. Torque will decrease.
When torque decreases, what happened to the speed?
It decreases.
This is what we are doing. When torque decreases, the load will be same. Then what happened to the speed of the motor? Decreases.
Yes, sir.
Understood?
I thought, yes, sir. I thought at the first step we have power consumption more strong.
No. Right? So
Okay,
for high speed, the power consumption will be more. For low speed, the power consumption will be less. It is like this. Understood?
yes, sir.
Right.
Sir, could you explain the reactive power? It's too confusing.
So reactive power, it is imaginary power. So there is no need to get confused. Your power system teacher will explain. Right? It is a part. Right?
Okay, sir.
So if anyhow, if you want tomorrow, I'll explain. Don't worry. Okay?
Okay, sir. Okay, sir.
Don't worry. I'll explain. Right.
Thank you, sir.
Right. Where is Sai Charan Reddy? Nowadays, he is not asking Sai Charan Reddy. Yeah. Bhaskar.
Hello, sir.
Ha, Bhaskar.
Sir, the in pole changing technique is not a variable speed control method.
It is step.
Only wide range of change ante only two speeds control చేస్తున్నాం.
Steps. It is not a regular. Just like your voltage, we cannot have a smooth control. Only steps.
Okay, sir.
Understood?
ఓకే సార్. అంటే ఏదైనా ఇప్పుడు కన్స్ట్రక్షన్ తర్వాత ఓన్లీ టూ స్పీడ్స్ నే కదా సార్ మనం చేంజ్ చేసేది?
అవును. Just only that stator construction is a separate construction.
Okay, సార్.
Okay.
With end rings connection changing 4 steps.
See, if you want to have 4 speeds, then what you need to do means you need 2 3 phase windings and the end connections has to be brought out. Like that we can get 4 speeds. Emma, Bhaskar.
Sir, okay, sir. From 12 to 6 we change side by side coil end connection. So how further we can decrease that?
See, a 12 pole stator can be changed into 6 pole stator, right?
Yes, sir.
By changing the end connections. This was already explained during the construction.
Yes, sir. There is side by side connection, sir.
Correct. By changing the currents in the side by side conductors. Correct.
Yes, sir. But how further we can decrease, sir, once construction is made?
That end connections are brought out. Now the tappings are brought out. So those tappings are available on the surface of that box. So by changing that, we can change. They are not internally done, but they are being brought out. Understood?
Okay, sir.
Right.
Sir?
Yep.
Sir, in auto transformer and star data transformer, starting torque is 1/3 decreasing now, sir.
In case of auto transformer, that value is not fixed. But in case of star delta starter, it is fixed.
Sir, it is decreasing 1/3 times now, sir.
In case of star delta starter, it reduces to 1/3. But in case of auto transformer, basing on your K, that will be varied.
Okay, sir. What is the advantage of this star delta, sir, compared to auto transformer?
The cost will be less, right?
Okay.
So the reduction in current and the reduction in torque both are same. But if you want to have a high starting torque, then which starters you need to go for? Auto transformer starters you need to go for.
Okay, sir.
Right.
Okay, thank you, sir.
Right. 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 I'll stop for today. So we'll meet after tomorrow. Thank you. Sai Charan Reddy is asking. Right, Sai Charan Reddy.
Hello, sir. Sir, the role of a dual starter in limiting the starting current, sir.
See, the dual starter is not used to limit the starting currents. Why? Because in the circuit, if you are having DOL or even if you are not having DOL, the currents will be same. But what is the additional thing we can have with a DOL starter means only during running condition to trip the circuit when the windings are more than the rated value. Understood? Why? Because for low HP motors, we don't need a starter. Why? Because those currents are flowing only for short time. The windings will be safe. But during running, so if you are overlooking and loading the motor heavily, then in that case we need to save the winding. For that we need a protection. That protection is there in case of dual starting. Sai Charan Reddy. Understood?
Sir, that 234 volts problem, we got an answer of 234 volts. Sir, I did not get that problem, sir.
What is the problem? See, what is the initial speed?
Yeah.
950.
950.
Now I want to reduce the speed by 10%, right?
Yes, sir.
So 950 in the 10% is how much? 95. Then I need to reduce the speed to 855 RPM, correct?
Yes, sir.
So if I want to reduce the speed to 855 RPM, I need to reduce the voltage, correct?
Okay, yes, sir.
So what is the voltage I need to reduce? Then I have to calculate V2. But the motor is driving which torque? Constant torque. So S into V square should remain constant. From that you calculate S2, V2.
Yes, sir. Yes, sir. Okay.
Understood?
Okay, sir.
Right. Right. I'll stop for today.